Well, I've been given the great pleasure of chairing this afternoon's session. Started with a talk on Feynman integrals, quasi-periods, and black holes by our friend David Broadhurst. Shall we get started?
Okay, well, thank you very much for the invitation. The organizers asked me to speak about high precision evaluations of Feynman integrals involving elliptics and beyond. And they also knew that I'd speak about the quasi-periods and intersection numbers of modular forms. But what they didn't realize was I also would like permission to speak about high precision determinations of the areas of the event horizons of black holes, which if you told me I was going to speak about that a year ago when we met at Potsdam, I would have been rather surprised. Now, the subject is really very limited. I'm just talking about four-loop sunrise integrals with 5-unit internal masses, and those give Bessel moments that evaluate periods and quasi-periods of modular forms, levels, very important numbers, 6, 14, and 34, and weights up to 4. Now, when the external mass in this four-loop sunrise diagram is unity, we're talking about contributions to the magnetic moment of the electron at 4 loops. And Stefano and Laporta and I really understand what's going there. And thanks to my work with Vadim Zudlin and with David Roberts, we understand that what we're doing is meeting the periods and quasi-periods of a modular form of level 6. And what I'm going to do is change the mass of that external particle. And if I set it equal to the square root of -7, now we understand what that means because we're talking the Minkowski norm of p squared will then be equal to -7. So I'm just evaluating a diagram in the spacelight region. Then we find periods and quasi-periods of a modular form of level 14. Absolutely astounding. And if we set it equal to the square root of 17 -4, is my pointer working, Jacob?
Yes, I can see it.
Thank you. There's quite a small number, comfortably away from any of the singularities of this of the differential equation which is underlying this diagram. We also we get to level 34 and determine the areas of event horizons of black holes, which are obtained from compactifying a 10-dimensional supergravity theory. For the experts, it's a type 2b supergravity theory in 10 dimensions with n equals 2 supersymmetries. But to get a 4-dimensional black hole, to get from the unreal world of string theory in 10 dimensions to the real world of 4-dimensional space-time, we need to compactify. And the compactification is on a calabi-yau threefold with complex structure, and wonderful to relate, the calabi-yau equation associated with that variety is the same calabi-yau equation as for the 4-loop sunrise integral. Okay. So now let me see if I can get to the next page. So now I should, at the beginning of a talk, define the mathematical objects that I'm concerned with. And I've done this on a single slide here, and I've done it in a way that would be perfectly comprehensible if I was so fortunate to be invited to a seminar in Leonhard Euler's group in St. Petersburg in 1760. Because I'm going to talk about Bessel functions, the moments of Bessel functions. Now, we all know that it wasn't Bessel that defined the Bessel function. It was Daniel Bernoulli 282 years ago in 1738. I hope I got that calculation in 1738, who showed that the oscillations of a hanging chain are described by a Bessel function. We now call that J0. And then here, I see the continuation of that, the Bessel function for I0 for real arguments is J0 for imaginary arguments. I see here Bessel function I0. Now the solution to the Bessel's equation, there are two solutions. This is the one that's well behaved at the origin, and this is the one which has a logarithmic singularity at the origin and is very well behaved at infinity, falls off exponentially. So what this is a Feynman diagram. If I put these little numbers m and n equal to 0, then I have 5 exponentially falling Bessel functions. Those are the 5 propagators inside the diagram. I'm integrating x dx, which tells me that I'm in 2 dimensions. X is the proper time from one vertex of the this 2-vertex diagram to the other. And the dependence on the external momentum, z squared, is going to be a real number, can be positive or negative in the space-like or in the time-like or space-like regions. The Fourier transformation with respect to the external momentum brings in another Bessel function. So this is these I couldn't explain in St. Petersburg in the 18th century, the quantum field theory that produces this, but these are perfectly easy to define and nowadays numerically to evaluate one-dimensional integrals. Now, what about these parameters m and n? Well, we understand what m is. It's the number of lines that I've cut. If I change one of these propagator terms and by putting it on shell, then I get the other solution to the Bessel's equations. What about this n here? Well, n corresponds to differentiating with respect to this external momentum z. But to show you that, I need to introduce this second family of Bessel moments, where I've differentiated once to get the derivative of a Bessel function. The relationship here is I differentiate with respect to log z to turn m into n. But then if I differentiate twice, because the Bessel function satisfies a second-order differential equation, then I get back to the m's but shifted. So we know that these satisfy differential equations. Not surprisingly, it's a 4th-order calabi-yau differential equation that we have down here. So really, we only need m and n, big M and big N, little n equals 0 and 1. Those 4 constants determine all of the higher derivatives. Okay, so those are the mathematical objects. But also, the heroes of this talk, a series of integers, very interesting integers. They enumerate something very important in lattice physics. But the first 3 of them are 1, 5, and 45. And they're generated by taking the 5th power of Daniel Bernoulli's Bessel function. He knew its expansion coefficients, they just involve x, coefficient of x to the 2n is 1 over 4 to the n times the square of factorial n. This is very, very convergent series. And so I take the 5th power of this, extract, take the power of x to the 2n, extract the powers of 2 and factorials, and define these integers. So what are these integers? I mean, they've come from Bessel functions, but what have they got to do with the Feynman diagrams? Well, you can see that the definition I've given gives this explicit formula, which is the number of self-returning walks of length 2n on a 4-dimensional diamond lattice. And that relates deeply to the condensed matter physics, and this is 4-dimensional condensed matter that I worked with John Borwein and with Larry Glasser. Of course, we would never use that formula when we look for a recursive definition. I give here the recursive definition in its most economical form that John Borwein and I derived 15 years ago. I define here 4 polynomials. Now they're quartic polynomials. They're actually quadratic polynomials in t squared. T is just a variable of that polynomial. And this is the recursion relation for those numbers. If I know 3 of them, I can find the 4th. It's a 3rd-order recurrence relation. And in here are just the integers. You see, I just substitute n and k down here. So it's a 3rd-order recurrence relation with degree 4, powers of m to the 4 down there. But the corresponding differential equation, you just shift degree and order. We have a 4th-order calabi-yau differential equation here. It's 4th order because it involves now fourth derivatives, and it's of degree 3 because it only involves x to the power 3, and you see down here. So this calabi-yau differential equation is the thing that the string theorists were interested in. And you can see that it's a fourth order differential equation, has 4 solutions. If I am at some arbitrary point x and I want to completely specify everything in the neighborhood of that point x, I need 16 numbers, the 16 periods of this calabi-yau differential equation at the point x. Okay. Now the map to Feynman diagrams is very simple. Their calabi-yau x is equal to 1 over the square of the Minkowski square of the momentum of the external particle. And the fourth order differential equation for Feynman diagrams comes from just the same polynomials down here, the same fourth order polynomials, involves powers of z squared, but the sunrise diagram itself with no cut lines satisfies the inhomogeneous differential equation. And here the right hand side of this equation is factorial 5. So what we've got down here is the Picard-Fuchs equations for the sunrise diagram, this external mass with 0, 1, or 2 lines cut. We can't cut more than that because the Bessel functions don't let us. So this is why we only need, even if we want to know all of the derivatives, you want to expand about this point, as people are doing in practical calculations. We just need 4 of these. We need, for a given value of m, we need m at 0, n at 0, m with 1 there and 1 there. And I give an example of how a higher derivative would occur. And so suppose that I know these 4 derivatives and I want to calculate higher derivatives, then I have to divide by this thing, which is cubic, because it's a cubic in z. So I have to divide by this cubic in z squared. I have to divide by these 6 factors. And I'm going to end up with horrible numbers when I do that. But now I tell you a very nice feature about this special point. Z is equal to the square root of -7. You can do this calculation in your head. Right, I want to evaluate this as square root of -7. Well, I have 1 plus 7, I have 9 plus 7, I have 25 plus 7, and I think you can do that in your head and work out that I have the 12th power of 2. So it's going to be very, very simple to develop these expansions at this point. Now, an even more remarkable trick is when the external mass is square root of 17 minus 4. This is a unit of the quadratic number field Q square root of 17. It has unit norm. If you multiply it by its reciprocal, you get its conjugate, you get -1. Conjugate just means changing the sign of the square root of 17. So we're going to have to divide by the norm of D if we're at this point. And now there's a wonderful trick. The norm of a rational function of u is the function times the conjugated function. And we can work out what the norm of this is, right? So down here, I've got 1 minus u. The norm of that will involve 5 squared minus 17, and I get 8. Now, I could do that for you for all of those, but now I tell you that I can immediately deduce that the norm of the number by which I have to divide in the quadratic number field is minus the 25th power of 2, a rather memorable number because we've got 10 fingers. The 25th power of 2 has a rather nice feature, 33554432. And that comes from the splendid quintic identity that this mass satisfies this quintic equation. And that's where the 25 comes from, because I have 3 powers of 2 from the norm of this, and I have 22, and I have 22 powers of 2 from the norm of this, and I have a minus sign from here. So it's hard to imagine better regular points of this differential equation. Of course, we know the really important point for the mass of the electron is z equals 1, but that's a singular point of the differential equation. These guys have discovered beautiful mathematics happening at a regular point of this fourth order calabi-yau equation. And the discoveries were by Philip Candelas, Zenia de la Ossa, Mohammed Elmi, and Duca van Straten. And they were working entirely on the calabi-yau side. Being good string theorists, they were totally oblivious to Feynman integrals. They never understood them. They've been told in their early days as string theorists that you should never waste your time evaluating the Feynman integrals because they to do with the quantum field theory of point particles, and the world is really made of silly little bits of strings. So they were completely oblivious of the machinery which we had developed at the singular point of this differential equation. Now, what they found is that these points down the calabi-yau side, x equals -7, and 33 plus 8 times the square root of 17, were very interesting arguments for the analytic continuation of the solution of the carbon-Lau differential equation. They had to do analytic continuation because the radius of convergence is only 1/25. We know physically there's a branch point at z equals 5. You can't, if you have a particle of mass 5, it can decay into 5-unit mass particles. So we knew, and that meant that I had to do some very slow and tedious Runge cutter integration. Of course, we don't have to do that. I was immediately able to transform, when I heard just this value, they just said x equals -1/7 is interesting, immediately transform all of their things to the Feynman diagram side. So now I go to that, and I go through the next 2 slides very quickly, relatively quickly, because I've talked about them extensively at previous conferences. But if you haven't heard this before, the magnetic moment of the electron has contributions from the on-shell sunrise diagram. So that's M00, and on-shell means external mass is equal to unity, 5 propagators. Now, of course, this has this wonderful representation in terms of the Feynman or Schwinger parameters that Karen was talking about yesterday. And here's a second semantic polynomial. It involves 5 parameters because there are 5 internal lines, edges as Karen would call them. It has this wonderful form down here. If I take out some powers of x's down here, I take the sum of the 5 parameters times the sum of the reciprocal of the 5 parameters and subtract z squared. You can see why, as long as z squared is less than 5, this is a perfectly well-defined integral. It's only when all of these x's become equal to 1 and z that we find a singularity. Now, in Stefano's calculation, what about these m's and these n's that I'm talking about? How many of these did he actually need? Well, at this singular point, first of all, we have to have the uncut diagram. We can only cut 1 line at this point. We can't cut 2 because this Bessel function, then I'll end up with 3 Bessel functions killing whose exponential behavior kills off the remaining 2 propagators. So I've only got these 2 things to look at. And you might think that I need for the diagram with 1 cut edge, I would need 4 numbers, but I don't. I only need 2 numbers because at this singular point, we see zeta values appearing. And the recurrence relation that became singular at that point also eliminates the other values of m. So we're only left with 4 numbers. And these 4 numbers have an intersection number. They satisfy a quadratic relation, which I discovered. So the sunrise diagram on shell, this is a second differential with respect to external momentum. This is with 1 line cut. This is with 1 line cut on a second differential. The determinant of this matrix is a multiple of zeta 4. Underlying this is modularity. And here we have a very explicit construction of the modular form. I take the Dedekind eta value. Now, tau is just like it was in the previous talks on modular forms. It's in the upper half of the plane. Q is the expansion parameter, exponential of 2 pi I tau. And this, with this marvelous factor of Q to the 1/24, is a modular form. And of course, we want things which have expansions and powers of Q. We don't want these 1/Q to the 24. Well, what you do, eta of n, I'm going to call eta of n tau, but I take eta of tau, and eta of 2 tau, and eta of 3 tau, and eta of 6 tau. Each of these has weight 1/2. So I want to weight 4 modular form, I square it, and is it going to be okay? Well, can you do that sum 1 plus 2 plus 3 plus 6 times 2 is equal to 24. So this starts off like Q. It's well behaved. It's a cusp form. It falls off exponentially fast in the upper half of the plane. where Q goes to 0. That's the modular form. But from work by Francis Brown and Dick Hayne, I know I also need a weakly holomorphic form, something with a singularity at one of the cusps, something that you will not find in the textbooks, because it will be the integrals of that which provide the quasi-periods that, together with the periods, give us the intersection number. So here it is. I constructed it. It took a certain amount of ingenuity. I took this very well-known modular form and I multiplied it by this function of W, where W is an invariant of of transformations of gamma 0 of 6. I don't know if you remember Stefan Weinziel's talk, and he talked about congruent subgroups. So down here, and this looks perfectly innocuous. I'm taking something that's very, very well behaved in the upper half of the plane, and I'm multiplying it by some of this Q expansion. But the price is that this W becomes 0 or infinity at 2 of the cusps. So it's a weakly holomorphic form. However, I've still got one cusp from which I can integrate. So the periods and quasi-periods, I take my modular form, I take my weakly holomorphic modular form, I integrate them from tau equals a half to I infinity, where they're perfectly well behaved. W is equal to 1 at tau equals a half and is equal to 3. And then I use a modular transformation. Do you remember yesterday's comments? I was saying, make sure you fully exploit modular invariance. And in the talk, in the second of the talks, we heard people very seriously exploiting modular invariance, but they were only exploiting SL2Z. Here there's a GL2Z, that is to say an integer matrix which doesn't have unit determinant. It's called an Atkin-Layler transformation, and it swaps cusps. And so when I operate it, what it does is it turns W into 3 upon W. So the integral I had to do from a cusp up to infinity, I can now do up to the fixed point of this transformation, which is 1 plus I of the square root of 3 upon 2, and then up to infinity. And then you see how I can calculate at the canonical Laporta rate of 10,000 digits a second. You know, the guys in Oxford can manage 50 digits a week, but we want, Stefano needed 20,000 digits of hundreds of integrals to do his parallel PSLQ to make analytic evaluations of the Feynman integrals contributing to magnetic moment of the electron. So that's how we get this this efficiency. And here now is Laporta's intersection number. I take linear combinations of these diagrams, I remove factors of pi, and I get the periods of the modular form and the quasi-periods of the modular form associated by its weakly holomorphic partner. And David Roberts and I have, as you've heard in previous talks, have conjectured explicit by Roman Lee and by Babas, have conjectured explicit forms of all such quadratic relations on shelf, all loop sunrise diagrams, and Javier Frezin and Claude Zappa and Yang Dor Yu have proven our formulas up to 20 loops. They ran out of computing, they ran out of combinatoric computing power to prove our explicit one-line formulas. So now what I want to do is to go to this space-like case, right, p squared equals -7, which engages level 14. Now, on the calabi-yau side, what we need is a Frobenius basis. Now, remember that Y0 is the thing with these lattice counting integers as its coefficients, but it's only one of the solutions. It's the regular one at the origin. The others will involve first, second, and third powers of the logarithm of x. They're the singular ones. It's a fourth order differential equation, so we can stop down there. But we can take out the singular parts of these other solutions, and we're left with the regular things down here. This is what the Frobenius basis is. And these have expansions about x equals 0, perfectly regular, and the coefficients of them are rational numbers, and we can very readily find that. And these guys want to get to z equals the square root of -7, and they've got a real problem, because the radius and convergence of this series is 1/25. You already know that from physicists, but you can work it out yourself. Even if you just count it, if you work out how many self-returning walks there are, and the walks get long enough, this number grows like 25 to the n. And I developed the asymptotic series that tells you that this function down here has a dilogarithmic singularity at x equals 25. Now, they don't want to go to x equals 25, they want to go to x equals -7, but that's outside the radius of convergence. So they had some very nasty, dirty work performed particularly inefficiently by Mathematica to do Runge-Kutta integration of this fourth order differential equation. Because as quantum field theorists, we've got no such problems. They're merely evaluating a Feynman diagram with a perfectly well-defined non-singular point in the space-like region. And we have it as a one-dimensional integral. Underlying this are the modular forms. Now, it took me the best part of a day to identify the modular form. From hearing in the afternoon, for hearing in the morning before a seminar by Mishy Berinsky in Oxford that x equals -7 was interesting, I was able to find out that what they were doing were calculating, among other things, the periods of this modular form of weight 4 and level 14, which I've constructed out of eta functions. And its periods are critical values of the L function. The L function is just the Eichler integral from 0 to I is infinity, suitably normalized. And we know from conjectures by Deligny and Grothendieck, eminent luminaries, that the critical values of this L function are related to the periods of the algebraic variety that is inside is the denominator of our Feynman integral. So we expect, and the numbers relating these that are conjecturally rational, but you normally calculate them by evaluating the left and right hand side of the equation and finding the nearest rational number. In fact, it's been proven, at least in the on-shell case, that the exact relationship between this Feynman diagram, the space-like point, with one cut or with two cut lines give me the L function at 3 or 2, and by Eichler-Shimura theory, the value at the critical integer s equals 3 is related to that at 1 with this part squared, which keeps the transcendental weight correct. But what's really interesting down here is that I'm in an elliptic case. Gamma 0 of 6 has genus 0. There's no modular curve of conductor 6 on shell, but here there is an elliptic curve. And it's very easy to find the underlying elliptic curve. Now, we as physicists know that all elliptic curves are quartic. It's only mathematicians who like to write them as cubics, because we typically encounter quartics as 2 square roots coming from Chilean functions. And, now, to find this quartic, it's very good because we already know the modular, we should be writing this in the upper half of the plane. So what I've written down here is an eta quotient. This is not a Haupt module because we're in genus 1, but it's an invariant of gamma 0 of 14. It's got this very nice Q expansion. This is going to be the X of my cubic equation, elliptic equation. And what's the Y? Well, I should differentiate X with respect to Q. Well, I differentiate it with respect to log Q. But hang on a second, when you differentiate a modular form, you increase its weight by 2. So if I just take this X, I've grissed out dx by dq, I've got to divide by some modular form of weight 2 to get a modular invariant and gamma 0 of 6. To make sure that my parameterization of the curve in the upper half of the plane has the correct modular invariance. And so I do that, and I evaluate that, and I only need to, you can do this by, derive this equation by hand. You only need to calculate up to here and up to here to find out that that's the elliptic curve. And of course, you can prove that's the elliptic curve because by modularity, this particular thing for 4 terms of the expansion constitutes a proof. You can verify it up to powers of q to the 1,000, and a mathematician will tell you you don't need to do that. An empirical determination like this that gives you a finite answer is a proof. Wonderful bit of combinatorics there. So the periods of this weight 2 modular form at level 14 are computable at lightning speed, not the 10,000 digits a second that Stefano and I want to know about, but the 100,000 digits a second that Gauss's process of the arithmetic geometric mean gives you. Here's this very interesting arithmetic geometric mean. I take 2 pi and multiply by the arithmetic geometric mean of these, and I get the 2 periods. Now, I've only got one L function. It's the subject of the Birch-Swinnerton and Dyer conjecture at the center of the critical strip for a weight 2 modular form. And this particular case, the Birch-Swinnerton and Dyer conjecture is proven. And one of the periods down here, let's call it the real period. I put plus and minus down here. The complex period that I get by taking these, taking this imaginary part with the minus sign, this defines a J invariant, and the J invariant of this curve is this. So you can find it in the dictionaries of people that like to write cubic equations just by looking for something with that J invariant. But these elliptic integrals are determined by Feynman diagrams. Now remember that we've got to cut one line or two lines, and they're determined by this and the first derivative with respect to the external mass before the external momentum, before we put p squared is equal to -7. One way of saying that is that we now know how to calculate these Feynman diagrams to lightning speed because we know how to calculate arithmetic geometric means. Now this is the stage that I was at in December when I met Eric Panzer in Padova, and he asked me a question that really shook me. He said, can you really derive all 16 calabi-yau periods from Feynman integrals? It looks impossible. I've only got 8 Feynman integrals I can talk about. And yes, I can, but only at these very special regular points. And so I can now tell you in the affirmative, I have evaluated all of them, all 16 are at these points and others at other points. And in fact, 6 of them are enough because there are 2 intersection numbers. We've heard a lot about intersection numbers. So the 16 calabi-yau periods are analytic continuations of the derivatives. And the quasi-periods associated with the modular form, they're just the complete elliptic integrals involve the third derivative, sorry, this is the value of the first derivative, the second derivative down here. And of course, Legendre told us all that time ago what the intersection number is. We just take the matrix of periods and quasi-periods of modular form associated with the elliptic integral, and here now is the intersection number. So that's got rid of one of my Feynman diagrams. And of course, what I'm expecting is to be able to do the same thing for the section number of the periods and quasi-periods of the weight 4 modular form, which will involve my 4th derivative. And it didn't take me very long to discover that this is the generalization of the Laporta matrix on shell at level 40, level 6 to level 14. Okay. And indeed, I can evaluate these as Eichler integrals of weakly holomorphic modular forms. So looking at the time down here, I can quickly tell you what happens at level 14. Again, I have 8 Feynman integrals. They satisfy 2 quadratic relations. The external mass is this. But now I need a Dirichlet character. Can you see how the whole machinery, which we've heard about in previous talks, which is for practical calculations with Feynman diagrams, is coming into play? Dirichlet character is a trivial one that tells me that if p is not equal to 17, the character is plus or minus 1 according as whether or not 17 is a square or is not a square modulo p, or Gauss tells me that that's the same as saying whether p is or not a square modulo 17. And there are 12 cusp forms. There were 4 cusp forms I'm sorry, this is a mistake. This is a very big mistake. We're at level 34 here. That's a very big mistake. So we're at level 34 here. There were four cusp forms, so already quite a complicated problem. Here I have 12 cusp forms. but I identified a pair of new forms, things that cannot be derived from lower levels like 2 and 17, whose Fourier coefficients are in a different number field. They're Gaussian integers, in other words, a plus ib when a and b are integers, and the two modular forms are related by complex conjugation. So the L values of these critical L values we're looking at are the analytic continuation of this L series, which we know for a modular form is given by an Eulerian product over primes, but here with this character appearing. And so we only need to know, and Paris-Pay will tell us for the first, all the primes up to 1 million or whatever it is, what these Gaussian integers are, and very beautifully, if p is a square modulo p, this is a real integer, and if it's not a square modulo p, it's I times an integer, and only at the very special prime that divides the conductor down here do I have a truly complex number. So I can evaluate, right, the Feynman diagrams that are involved, and because of modularity of the L functions, and find, but now the linear conjectures tells me that these things should be related, if these are, as I can, the calabi-yau periods, should have numbers, not rational numbers now, but numbers, biquadratic numbers in square root of 17 and the square root of -1. And so these are the numbers I determined empirically. It doesn't take very much PSLQ to find numbers like 13 and 1. And what that means is that I've now evaluated 2 of my Feynman integrals in a highly efficient way, 10,000 digits in a few seconds. And also, down here at weight 2, I expect to have the periods and quasi-periods of a elliptic curve. And here I've written it in a very nice cubic form. It took quite a while to write it in this form. If u is equal to z, these are at the zeros of this polynomial, which factorizes in this quadratic number field, telling me that there are singular points of the differential equation at z equals plus or minus 5 and z equals plus or minus 3. Here are the real and imaginary periods. I'm just doing the same thing before. Here I have 100,000 digits a second. And here is the empirical relations that I have between the easily calculated elliptic integrals and the relatively easily calculated Feynman diagrams. And now in here we have coefficients which are integers in a quadratic number field. These would look pretty horrible if I start expanding out these factors, but we have a unique factorization domain. And here's Legendre's condition. So, looking at time, I'm bang on schedule. All I had to do to solve this problem was to find the quasi-period associated. Here are the periods of the modular form, and here's my determinant of the quasi-period that satisfies this intersection number. So what has it got to do with black holes? Feynman integrals determine the areas of the event horizons of black holes, which are specified by charges. These black holes come from, as I said, from taking a type 2B 10-dimensional supergravity theory, 2 supersymmetries, compactifying it on a calabi-yau threefold with complex structure, the calabi-yau threefold associated with the second semantic polynomial of the sunrise diagram. Wonderful to relate. And the area of the black hole that they get, specified by these charges, it's multiplied by 34 pi, which looks like a pretty sensible number to multiply by at level 34. And there's this number v. Now this number v comes from these critical L values. But the way it appeared in their thing was absolutely horrible because they didn't know about Feynman integrals, you know. So they had, when they expressed the number v, they had all sorts of nasty factors of I and pi and square root of 17 and goodness knows what. But in fact, this v is just a ratio of 2 Feynman integrals. So I take the sunrise diagram, I put the mass equal to the square root of 17 minus 4. I cut 2 internal lines and 1 internal line to get a number of transcendental weight 0. I jolly well better multiply by pi. So there are only 2 numbers that you have to calculate if you know about Feynman diagrams. You can calculate these to thousands of digits of accuracy, but you only need a couple of digits to work out that this number here is 4. And this number 34, I take no responsibility for. These are the experts down here, they tell me. Now, what do you think happens when I go to the spacelight point? Well, I don't think it takes too much ingenuity to know that this number turns into 14. And so, down here, I go to p squared equals -7. I put u is equal to the square root of -7 down here. And so I had one number to calculate in that particular case, and it turned out to be 2. Now, what I was able to do, as well as show how beautiful these areas are, was to identify 6 constants they lack. There are 48 constants around down here, because there's 4 solutions up to 3rd derivative, and the neighborhoods of these points, and they were lacking 6 of these constants. And I was able to, I knew what they didn't know. What they didn't know was that Dick Hayne and Francis Brown identified these numbers from the permanence of the matrices of Feynman integrals. Feynman integrals to me, whose determinants goes the intersection numbers. So I knew what numbers they were missing. They're really only missing 4 of them because the numbers they were missing at plus the square root of 17 were related to those at minus the square root of 17, though they weren't able to prove that. And in this work, I was greatly aided by my work with Kevin Akers on Rademacher sums, because the Rademacher sums are what determine the permanence. When I have a matrix, when I say down here, of course, I can add any multiple of this and still get the same determinant. But that special number down there, that is relevant for the permanence of this matrix, which is where I take the plus sign down there, then it really matters. And so there's quite a lot of theory underlying 81 and similarly for the level 14 case. So I conclude, Xenia and Philip and Mohammed and Duco made this absolutely amazing discovery. It's totally theirs. At the level of mathematics, that a calabi-yau equation, which we already knew gave periods of a level 6 modular form at a singular point, also gives periods of modular forms of levels 14 and 34 at regular points of that equation. I mean, something which I don't think, it ought to have surprised the mathematicians. It absolutely astonished Stefano and me. But you see, Laporta and I, and along with David Roberts and Anton Mellet and Yajun Zhao, we completely mastered the mathematics of the level 6 case because, you know, this is a matter of real importance in quantum field theory on the Feynman side. So I was in this happy position of being able to bring the expertise from quantum field theory to bear on unsolved calabi-yau problems at levels 14 and 13 from the string theorists. And the 48 constants that they wanted are completely determined by my 16 Feynman integrals, which satisfy 4 quadratic relations. And then, to honor my promise to the organizers to talk about high precision, then in a space of probably, I'd like to say a few minutes, but one of these might have even taken an hour. I computed all 16 of these Feynman integrals to 10,000 digits, just using series expansions. Because my expansion parameters, this was the expansion parameter for the periods and quasi-periods at level 14. And at level 34, I used a mixed approach because here, down here, we're very close to x equals 0 if we take the minus sign down here. Remember, the expansion parameter is really 25x, but 25 times 33 minus 8 times square root of 17 is a nice small expansion parameter. And now I conclude, thanking you for your attention, with a sentence that I truly did not expect to communicate at a conference of this kind, namely that 2 ratios of Feynman integrals determine the areas of the event horizons of black holes from compactification of 10-dimensional supergravity. And thank you very much for your attention.
Thank you, David. We have time for a couple questions. Please raise your hand. Okay, well, I don't see any questions. Why don't we thank David once more, and ready for the second talk of the session. Thank you, David. Okay, our second speaker this afternoon is Matija Tapušković, who will tell us about Motivic coaction and cohomology with twisted coefficients. Can you share your screen?
So first of all, thank you to the organizers for inviting me to give this talk. I think, so we're going to talk about the Motivic coaction and its interplay with dimensional regularization by using cohomology with twisted coefficients. This talk actually is a nice addition to Ruth Britto's talk from Monday. In fact, I also used as the same example throughout. So, okay, so let's start with some definitions. First of all, we'll be considering Feynman integrals in parametric representation, which are integrals of this form, where G is a Feynman graph with VG vertices, EG edges, and EGX legs. D is the number of space-time dimensions, NG is the number of internal edges, and AG is the loop number of G. Now to each edge, to each internal edge EG, we associate a variable alpha E and define the first and second Szymanczyk polynomials. The form omega G in the integral is the standard form on projective space, and the domain of integration is the standard simplex in P in the projective space of dimension ng minus 1, that is the real points of that. We'll only consider convergent integrals for now, and also note that I have dropped the gamma value, which usually goes in front of the integral. And crucially, note that these integrals are families of periods, meaning that they're integrals of algebraic functions over algebraically defined cycles of integration, which vary as functions of the kinematic variables. So now I want to set up some technical details for the Motivic-Galois theory of periods. This will be brief, and we'll soon see some examples how this works with Feynman integrals. So sorry if this is a bit too technical at the moment. So we'll be considering the category H of S of triples, where VB, B stands for Betty, is a local system of finite dimensional Q vector spaces on the complex points of S. V Daram is an algebraic vector bundle on S with a flat connection with regular singularities at infinity. And C is an isomorphism of analytic vector bundles with connection. We also require that V Betty underlies a variation of mixed Hodge structures, that is, that we have Hodge and weight filtrations compatibilities with C, with the comparison C, and so on. Crucially, H of S is a Tannakian category with two fiber functors, omega Daram gen stands for generic, which sends an object of H of S to the sections of V Daram over the generic point of S. I should say that S is here the space of kinematics. That is the complement in the space of kinematics of the Landau variety, but anyway. Omega Betty is another fiber functor which sends a triple to the sections of the local system V Betty over a simply connected open subset of the complex points of S. With this in mind, we can define the ring of Motivic periods as the algebra of functions on the torsor of isomorphisms between these two fiber functors. We can see the elements of the ring of Motivic periods as triples V sigma omega, where V is an object in the category H of S. It's a triple again, and sigma is a section of V Betty. That is, it's a cycle of integration or a family of cycles. And omega is a section of V Daram. That is to say, it's a differential form or a family of differential forms, more precisely. Now, this ring is endowed with an with a period morphism, which lands in the ring of multivalued meromorphic functions on S of on the complex points of S with the prescribed branch along Z. Now we can define the motivic Galois group, that is its de Rham realization, as the group scheme of automorphisms of the de Rham fiber functor. This group scheme acts on the ring of motivic periods, or dually, it coacts by its algebra of functions. Now, crucially for Feynman integral applications, Brown in 2015 associated to any Feynman graph with generic kinematics a graph motive, which is an object of this category, H of S, and an element IMG in the ring of motivic periods, such that the period, its image under the period map is the integral, is the Feynman integral itself, with its dependence on the kinematics. Now, we call IMG the motivic lift of the Feynman integral, or the motivic Feynman amplitude, as Brown calls it. Okay, so now for an example. With this in mind, we can consider a box graph like this, with all masses and momenta generic in D equals 4 dimensions of spacetime. We can then state a theorem about the coaction, computing the coaction. And in this theorem, I only want to focus in this talk on the left-hand side here. So these numbers in red, these motivic periods in red here are the motivic Galois conjugates of the motivic Feynman amplitude of the box graph. And by this notation, I mean that they are motivic periods associated to the Feynman graphs, which we obtained by contracting two edges of the box graph. And also D equals 2 stands for the fact that these are the motivic Feynman amplitudes in D equals 2 dimensions of spacetime. Crucially, we note that these motivic periods are associated to subquotient graphs with fewer edges than the original graph. So we can then reasonably ask when a statement like that for Galois conjugates is true, or more precisely, is it always true that the conjugates of a Feynman integral are motivic periods associated to motives of subquotient graphs, with weight of the conjugates bounded by the number of edges of the subquotient graph? If so, this is a very powerful statement. It relates the integral that we started with to the integrals associated to subquotient graphs, thereby providing information and constraints on the original integral in terms of the simpler integrals. Right, so let's consider another example, which is the one from Brito's talk. So we take the 3-point function with one loop, and all internal masses are set to 0, and the external momenta are generic. This is the relevant computation of the motivic coaction on this graph. And again, let's focus on the motivic Galois conjugates on the left here. These are the motivic lifts of logarithms of these quotients, and they're not motivic periods associated to quotient graphs, not directly at least, which is very much expected because the quotient graphs, for example, this one where we contracted the edge number 2, do not converge when the internal masses are 0. Right, so clearly we need to regularize, and we consider dimensional regularization. We set 4 minus 2 epsilon dimensions in our initial definition of the Feynman integral, and we let epsilon vary. That leads to an integral like this. And now we can expand in epsilon and obtain an expansion here, which I call IGL. L stands for local. And we can write the logarithms in the expansion here as algebraic integrals, and therefore see that coefficients, that all coefficients in epsilon are themselves periods. So we can apply then the coaction term by term in epsilon. I put the red M here because I'm assuming that I've lifted the coefficients to the ring of Motivic periods so that I can apply the coaction. And a priori, I get a series in epsilon with coefficients which are tensor products of Motivic periods and functions on the Motivic-Galois group, which I'm not going to worry about in this talk. However, the claim is a very strong claim, is that this series actually can be rearranged so that it can be written as a product of two series in epsilon, one having coefficients only Motivic periods and the other having coefficients, the functions on the Motivic-Galois group. In fact, the conjecture is stronger than that. And in their paper, Abro, Brito, Duran, Gardi, state that it can be rewritten in terms of quotient graphs. Now, in blue here, this is the trivial term. I'm going to ignore that. In red, I have the expansions in dimensional regularization of quotient graphs, that is of the bubble graphs that we just saw by contracting one edge of the triangle. And in gray, we have the functions on the Motivic-Galois group, which I would just note that in their conjecture, the Abro, Brito, Duran, Gardi state that these can be related to cut graphs, which would be wonderful, and is actually in the one loop case can be very likely can be made rigorous for the higher loops. I'm not sure. Okay. So let's try to, sorry, I'm just going to go back. So now let's try to make sense of this formula at the bottom here using cohomology with coefficients. First thing that we do is fix epsilon to be a generic number. In this case, it's not, we require it to not be a half integer. Now this is a bad thing to do essentially because we want to be able to expand these integrals around epsilon equals 0 usually. But let's go with this for now. First, we want to realize the integral as a period. And period here is in inverted commas because by introducing this epsilon, we are exiting the world of classical periods in the sense of Kontsevich and Zagier. Okay, and let then Q be the vanishing locus of the second semantic polynomial of the triangle graph, and L be the vanishing of the first semantic polynomial, and let them be defined over a subfield of C. That is, we fix the kinematics, we fix the kinematic variables. Then consider a vector bundle, O of X, a rank 1 vector bundle, on the space which is the complement of Q union L in the projective plane with the following connection. Then let L epsilon be a rank 1 local system of flat sections corresponding to the vector bundle just defined. By this I mean there is an isomorphism like this one. And then there is a comparison isomorphism. This is a relative version of a theorem of Deligne, where we have an isomorphism between the Twistor de Rham cohomology with coefficients in this vector bundle and the Betti cohomology with coefficients in the local system. D here is the divisor given by the coordinate hyperplanes in P2, that is the coordinate lines, minus the points of intersection with, oh, it's written X here, it should be Q, minus the points of intersection with Q and L. Okay, with all of these defined, we can see that the differential form omega over psi squared, which figures in our integral, is defines a class in the Twistor de Rham cohomology, and moreover, the domain of integration sigma g, loaded with the function psi squared over psi to the power epsilon, defines a loaded cycle that defines a class in the in the Betti homology with coefficients in the local system L epsilon dual. Dual here is because we've passed from cohomology to homology. In fact, to be completely precise, we need to replace Betti homology with locally finite homology. This is because some points of the domain of integration, sigma g, were deleted. We'll see that in a moment. Were deleted when we deleted Q and L, the graph hypersurfaces. And in this case, we can do this replacement. We can replace Betti homology with locally finite homology with impunity, for a reason that I will describe in detail in a moment. With all of that in mind, the integral I of g, which is now the dimensionally regularized period, is a coefficient of this comparison isomorphism. And this is what we mean when we say we realize the integral as a period. We write it as a coefficient of a comparison like this. Okay, so now let's study the motive, the relevant motive. And motive again is in inverted commas because we are not in the classical setting. First claim is that this motive sits in a short exact sequence like this. The reason for that essentially is the following lemma that which states that the cohomology of the complement of Q union L in P2 with coefficients in the local system L epsilon is concentrated in cohomological degree 2 and has rank 1. Now, the sequence itself is a long exact sequence in relative cohomology where the lemma implies the 0 on the left. That is that the first cohomology of X with coefficients in L epsilon vanishes. The 0 on the right is implied by Artin vanishing essentially because the space, the coordinate lines minus the points of intersection with the graph hypersurfaces are an affine space, are affine spaces, and therefore everything above H1, above the dimension, vanishes. Okay, so because this lemma is it's a crucial tool which makes the cohomology with coefficients so useful and sort of easier to work with in a certain way than the standard one. I'm going to go into a brief sketch of the proof of this. So let J be the natural open immersion and the inclusion of X into the projective plane. Then if epsilon, as we've required, is not a half integer, we have this isomorphism of local systems. Actually, it's an isomorphism of in the derived category of sheaves on P2. It's much more. It's more general. It's true whenever the monodromy of the relevant local system doesn't have 1 as an eigenvalue. Now, essentially, because of this isomorphism and because of how cohomology with compact support is defined, we have an isomorphism between the cohomology of X with coefficients in the local system L epsilon and the compactly supported cohomology of X with coefficients in L epsilon. Now we can apply Poincare duality, which is stated here in the generality that we needed in, which is to say for cohomology with coefficients in local systems, and by Artin vanishing, which is stated here that I just mentioned before. So everything above K equals 2 vanishes. These two together imply the first statement that the cohomology is concentrated in degree 2. Now, the fact that it's rank 1 comes from this very easy statement that the Euler-Poincare characteristic of twisted cohomology with coefficients in a local system is equal to the rank of that local system times the standard Euler-Poincare characteristic of the space. In this case, this is just 1. Right, so actually point 2 here is very important because from it, it follows also the statement about replacing homology, with locally finite homology, with impunity also follows. Also from that, intersection pairings and other interesting things that people have been studying recently in the context of quantum field theory and string theory has been, it also follows from that. Okay, so back to the motive. This is the short exact sequence that we're looking at. Now let's look at the left-hand side, or what are known as the boundary motives. Now these are, if we look at how they're defined, they are isomorphic to H1 of P1 minus 3 points with cohomology in this local system that we've defined, except we're restricted obviously to the boundary. We can notice that this is a beta motive up to a twist. By this I mean essentially it's a rank 1 motive whose period is what I've written here. It's a beta function evaluated at minus epsilon, comma minus epsilon, with a prefactor of a momentum square of momentum squared to the power of minus epsilon. For much more generality in this direction, you can see a very nice article of Brown and Dupont from 2019, which studies generalized beta integrals in this generic setting with these fixed generic parameters, and also talks about the coaction there and so on. Right. On the right-hand side of the short exact sequence, we have this object H, second cohomology of the complex of Q union L in the projective plane with coefficients in L epsilon, and I claim that it's a C to the power epsilon twist for a constant C. Constant C is a rational function of the momenta, which I didn't write it here. Of a pure Artin Tate motive of weight 2. This just means that it's isomorphic to the standard Tate motive of weight 2 multiplied by C to the power epsilon. After a finite extension of the field of coefficients, that is, which just comes from the fact that Q and L intersect in a non-algebraic, in a point that's, in points that live in a quadratic extension in this case. Of the field of coefficients. Anyway, let's look at the period matrix for this motive, which is much more concrete than what I just said. On the diagonal here, we have the beta functions that we've just seen, multiplied by an epsilon power of the momenta squared, minus epsilon power. Why is it? Oh, it's minus epsilon. Yes, this is fine. Right, these correspond to the boundary components, and then the zeros above the diagonal are there because we have a direct sum of twisted beta motives on the left-hand side of the short exact sequence, if you remember. In the column on the right, we have 3 integrals, I1 to I3, which could be integrated directly, but we don't need to do that because we're just talking about the Galois coaction. So I'm going to skip that for now. And finally, in the bottom right, we have the C to the epsilon times 2 pi I. This corresponds to the Artin Tate twisted motive that we've just seen. Okay, now the Feynman integral is a linear combination of the I1 through to I3 with coefficients, again, rational functions of the momenta. Now, we didn't define a Galois group and an action in this setting, but we could have done, and you can see Brown and Dupont for an ad hoc definition of the Galois group for this setting. However we defined it, the conjugates of the Feynman, of the dimensional regularized Feynman integral would be precisely these beta functions twisted by the momentum squared to the power of minus epsilon. And of course, there will be a trivial term that will correspond to this C to the epsilon times 2 pi I. Now, this is because essentially that's how Motivic Galois groups work. The conjugates will always be found in the Motivic periods the material periods in the coaction will always be found in the period matrix of the given associated to the given motive. Now let's expand, even though this is an illegal move now because we've fixed epsilon to get to this period matrix. But for the sake of argument, I don't know. Let's expand this expression of q squared to the minus epsilon times b minus epsilon minus epsilon, beta minus epsilon minus epsilon. On the left, we get the first two terms look like that. For the beta, the first two terms look like that, and we get something like this minus 2 over epsilon plus 2 log of qi squared, and so on as the first terms in the expansion. Now this was observed, although I might be wrong about a factor of 2 here, and possibly a minus 1, but maybe I was a bit careless there. But in any case, the shape is correct, and this was observed by Abro, Brito, Duran, Gardi in their paper to correspond to the first few terms in the expansion of the bubble integral with trivial internal masses and in Dirac. Right. The reason this is true can be quite obvious if we look at the geometry associated to the triangle graph. So here we have the quadric Q, which is the vanishing locus of the second semantic polynomial, and a line L. Now, the three coordinate lines here are given by the vanishing of the coordinates alpha, and it's very important to note that the quadric Q goes through the corners here. Now, each of the coordinate lines corresponds to the geometry associated with the three bubble integrals when the internal masses vanish, that is. This is due essentially to the factorization properties of the semantic polynomials. Okay, now let's have a quick look at a broader picture and what needs to be done in order to kind of complete this line of reasoning. So we started with objects like this one here, the cohomology of x comma d, where d is a divisor in x, with coefficients in some local system L epsilon. However, we fixed the epsilon to be a generic complex number to do our computations. And in fact, what we want to do is to be able to expand in epsilon. So we need to make epsilon vary, and this leads to a concept we call global Mellin motives. This is because it addresses its period. Their periods are integrals like the one on the top right here. F to the epsilon can be replaced with multiple functions as well. It can be f1 to epsilon 1 through to fn to epsilon n times omega. Omega is a differential form, obviously. Now, the reason they're called Mellin motives are because the periods are of this form. But if we allowed the kinematic variables to vary as well, then those should probably be called hypergeometric motives. The motives associated to those periods should be called hypergeometric motives. Now that we have epsilon that varies, we can take an expansion around epsilon, and this leads to the concept of local Mellin motives, whose periods are the expansions on the right here. Now, both of these, both global and local parts of the picture, should correspond to Tannakian categories, should be the global Mellin motives and the local Mellin motives should be Tannakian categories, each of which has a Tannakian Galois group attached to it, with a functor localized between them, which should enable us to compare the coaction before and after expanding in S. This is what leads to the this should lead to our ability to resum the series in such a way that they factor, like we talked about before. This is a topic of upcoming joint work with Francis Brown, Clément Dupont, and Javier Frezan. The local picture is already fairly well understood, but in fact, this category of local Mellon motives is very closely connected to the classical category of motives, or classical conjectural category of motives. While the global picture is much more out there, kind of. In any case, there is no reason for this to be limited to one loop graphs. As you can see here, any integral of the sort on the top right will do. Right, however, when we go beyond one loop graphs, I would say that it should be more difficult to interpret the right-hand side of the coaction. That is the coaction. That is the functions on the Motivic-Galois group that appear there. This is to do with the cut graphs in the conjectures of Abro, Brito, Duran, Gardi. Okay, so I've basically explained the main points that I wanted to explain. So I just look at another for the final few minutes. I would just look at another example of this phenomenon. So this also appears in several places relating to hypergeometric motives. This example, which is this integral from 0 to 1 of x to the power s a dx over 1 minus ax, where a is a fixed complex number that's not 0 or 1. The expansion here is when we expand this integral around s equals 0, we get this infinite series of polylogarithms. And okay, so this integral, by this integral I mean the integral 0 to 1 x to the power s a dx over 1 minus ax, is a period of this motive M here, where ls is this is not written well. Ls here corresponds to the vector bundle ox, and the connection is d plus s times, this should be d log x here, on the space a1 minus the inverse of a. Now this motive sits in a short exact sequence like this. We essentially, one does the same analysis, the same analysis that we did in the triangle graph case, and we finds that this motive sits in a short exact sequence like this, and moreover that the period matrix looks like this. So here again in the bottom right we get this twisted 2 pi I twisted by some constant to the power minus s here. Should be minus s. No, that should be s, I think. Anyway, let's look at the local expansion and see what happens term by term. If we lift the expansion to Motivic periods, just assume that we've lifted it, and we coact term by term on these polylogarithms here. The coaction of polylogarithms is well known by the work of various people, Contra, Vihara, Brown, and so on. And moreover, we also must coact on S by dividing it by this L de Rham inverse. Now, L de Rham is Elderam is one of these functions on the Motivic Galois group. And in this case, we have also removed the kinematics completely. We're not talking about Feynman graphs anymore. We've fixed S in the previous construction to be just a point. So if we do this and we apply the coaction on polylogarithms directly, we get an ugly formula like this. However, then the claim that I was talking about, the claim that it factorizes, leads to the following. We can notice that this can actually be rewritten with just two terms. One tensor, the RAM version of the same thing defined up here, and then the original series, the original local expansion tensored with this here. This thing on the right. These are again the functions on the Motivic Galois group. Now we have defined here this twisted AS local expansion with the RAM logarithms. The important thing to notice, well, two things. One is that these two terms exactly correspond to the Feynman, to the period matrix that we've just seen. It was a 2x2 matrix of the motive with twisted cohomology. And the second is that we also coact on this expansion parameter S. Sorry, by the way, for switching epsilon for S in the middle, at the very end here. But this didn't have anything to do with Feynman integrals, so I forgot to change it. Anyway, this S is clearly also an object that must be coacted on, and that's because it also belongs to this category of objects which are the functions on the Motivic Galois group. And in fact, from this expression, we can conjecture that it's of weight -2. This is in fact understood by now. We know why, and it is it is an object like that of weight 2. Yeah, I'll just conclude by saying that this is something this is a set of ideas that coming from Feynman integrals in dimensional regularization that's very exciting from the algebrogeometric point of view, because we have the situation where the coaction on infinitely many periods, like in this equation on the bottom, we have infinitely many periods, but it's can be rearranged into a finite expression and understood using these very convenient tools of cohomology with coefficients. So, okay, that's it. I would stop there, and thank you very much for your time.
Thank you, Matija. We have time for a couple questions before the break and discussion. I see Eric. You have a
Hello.
answer?
Hi. Can you hear me?
Yep.
Yes, I can.
I was wondering. So you explained that. So in the triangle example, I understood that without the dimensional regularization, the problem is that you don't have periods associated to the bubbles to match to the coaction, right? And once switching on the dimensional regularization, this works with these beta motives. Now, in general, I was wondering the fact that all these terms in the coaction are associated to quotient graphs. I mean, is there a general expectation that this should always be the case? Because I could imagine situations where you have two independent periods, say, or a higher rank part that does not come only from boundaries.
Right. So the question is, yeah. So indeed, so this is the problem with the coaction without dimensional regularization, with the triangle with internal masses vanishing. What happens is that the periods move away from the boundary, kind of, they jump somewhere else in the cohomology of the relevant motive. So I suppose what you're asking is does dimensional regularization move all the periods back to the boundary, and why would we assume that? Well, I'm not sure, to be honest. I would think that the fact that well, these factorization properties of the semantic polynomials, I think, show that you should always have the periods on the boundaries, except that sometimes these will diverge, so they won't. Yeah. So anyway, if you think about if I think about it in terms of periods and this geometry, I can't see how I could have periods moving away from the boundary because of the subquotient divergences. Or do you have in mind something different, where periods appear for some different reason, appear in the
I was thinking of a situation just where I don't know, I have a very complicated geometry, I have a very high rank, and maybe I don't have a super complicated boundary. So I just think in general.
Oh, I see. So okay,
convinced that I have enough stuff from the boundary to fill out everything.
Yes. Okay. So let's see. So already in the sunrise graph example. So for the sunrise graph, there will always be two periods that don't come from the boundary. There will be two. So because the cohomology of the elliptic curve, that is given by the second semantic polynomial in the sunrise case, because the cohomology of the elliptic curve is rank 2 and not rank 1, there will always those two periods will always be, they won't be on the boundary, obviously, and so yes, then in that case the Motivic Galois conjugates you won't be able to write them in terms of the subquotient graphs. They're just related to the graph itself, to the original graph itself. It's kind of difficult without being able to write. Is this an example like what you had in mind? Yeah, okay. In the chat, yes, thank you.
We also have a question from Ruth.
Mm-hmm.
Ruth, go ahead. Ruth, your microphone is on. Okay. Well, seem to be having some technical difficulties there. Another sec. For the break and discussion.
Okay, can I?
And
because I cannot raise my hand since I'm an organizer.
Oh yes, please.
Hi, Matthias.
Hi.
So I was wondering. So at the end of your slide, you mentioned these global, local Mellin motifs.
Yes.
And the definition you showed, I mean, at least, so I don't know much about the topic, but it looked very similar to what other people call these like motivic gamma functions. So is there any connection to that? Or?
Yes, there is a connection, but so this story is oh, there's Ruth. Okay, so I'll answer Claude's first, and then I'll come back to Ruth. Yes, they're the same they're the same types of integrals in both settings. However, there is, so if we look at, for example, a recent paper of Spencer Bloch and Masha Vlasenko on these gamma function and a priori constants and so on, these a priori numbers and whatever, this is a slightly more general, no, not slightly, this is a more general, it's a more general setting than what I was talking about here. They kind of generalize and then specialize to to something else. However, these things are related, and it could be. I don't have a very good, without talking about relative completions of fundamental groups and things like that, and of spaces. I can't really explain where the generalizations and specializations are, but yes, the answer is that there is definitely a relation. This should be simpler. This way that we're looking at it should be simpler to understand at first. I mean, I'm fairly confident that, for example, for Feynman integrals, we can write down motives, these new Mellin motives of Mellin motives associated to Feynman graphs, and that should be pretty straightforward in terms of the geometry that and graph hypersurfaces and so on, things that we're used to in projective spaces. So that would be the comment for that. Is that okay?
Yeah, thank you.
Okay, and for Ruth, I just wanted to ask whether there are particular obstacles looking at elliptic integrals. No, there are no. So as I said, any integral of the shape that I've shown works. So in particular, any Feynman integral in DIMREG. It won't be as easy to write nice expressions for the coaction for elliptic integrals because of two things. One that Eric mentioned. So for example, you will have multiple periods you could have multiple periods as the conjugates that are related to the original that don't come from the boundary, therefore they can't be expressed in terms of subquotient graphs. That's one thing that we have to kind of come to terms with. And the other is that the Duran periods, the right-hand side of the coaction, and expressing and relating that to actual integrals and not just functions on the Motivic Euler group, that step might be also a bit more, no, it will be more tricky because, well, there are technical reasons.
Okay. Well, let's thank Matija again, and we will return to hear a talk by Matthias Volk at 16:15.
Thank you.
Thank you.
Matija, maybe I can ask you a question as well.
Oh, sorry, real quick.
Oh, but that's okay. I mean, I didn't want to. It's just so. What I mean, it's not. You can have you could have left-hand entries that are not related to quotient graphs. Also, if it's not elliptic, right?
Yeah.
Okay. Okay. Great. Okay.
Yeah.
It's nothing to do with it being elliptic or not, right?
No. Absolutely.
Okay.
Yeah.
Okay.
What Eric said. Anything that where not much comes from the boundary, it kind of has a rich geometry just directly associated to the, for example, to the graph hypersurface. That is.
Okay. Okay.
So not the domain of integration and its intersection with the graph hypersurface, but the graph hypersurface itself. If that has a rich geometry and a cohomology of high rank, then whatever the rank of that is, that will be the number of periods that you relate to the subquotient graphs. Yes.
Okay. Okay. All right.
Jacob, can you hear me?
Yes.
There was a question from Stefano, but he was having difficulty raising his hand. We older people are not very. So Stefano asked a question of my talk, which I'd like to briefly answer here because it's a fascinating one to me. And that is that we're looking at regular points of the calabi-yau differential equation where there's extraordinary modular properties. Why are there just two of them? Why just these two algebraic numbers? Could there be more? And there's been quite a lot of investigation of that. And we do it by looking at the local factors of the primes of the L functions in the generic case. When the parameter is any algebraic number, and you look to see whether or not you have factorization of the local factor, which we do in the modular case. And so they investigated a huge number of rational and algebraic numbers, and they only found these two special values, the ones I began my talk with. So I think we have an extraordinary situation. I mean, it's something I think unexpected by the algebraic geometers as well as by the Feynman diagrams. It's been very thoroughly investigated. If you find another one, please tell me.
Okay. Thank you, David.
Any other questions for either of this the first session's talks? Okay, if not, we will reconvene at 16:15. Thank you, everyone.
I guess it is my pleasure to invite our next speaker to start sharing his slides. We have Matthias Volk here, going to tell us about the geometry of Feynman integrals and Twistor space.
Yeah, okay. Thanks a lot for the invitation to present at this very nice conference. So I'm going to present this paper here from May that was written together with Christian Vergu from Copenhagen, and that's also building on top of previous work and still ongoing work with Jake Berjali, Andrew McLeod, Matt van Hippel, and Matthias Wilhelm. So the title is Geometry of Feynman integrals in Twistor space, and so basically what we're going to do is we're going to analyze the geometry that we can associate to a certain class of Feynman integrals. And yeah, contrary to what we see now, we're going to do this in momentum twistor space. Okay, so for the context here, of course, we're interested in Feynman integrals for scattering amplitudes. For example, we can imagine a really nice theory like n=4 super Young mills. And as it's well known, if we look at simple amplitudes, then many times they can be expressed in terms of relatively simple functions. So in particular, these multiple polylogarithms that we've also seen a lot now over the week. So these functions, they're of course relatively well understood, although maybe it doesn't necessarily mean it's very easy to work with them, but at least the definitions are kind of clear and so on. But it's also, okay, the whole point of the week is to discuss about the fact that we need more complicated functions, and that when we make more complicated scattering amplitudes, that we are going to expect more complicated integrals. And many of these more complicated integrals, then they often have some interesting geometry, as we've seen now so many times, in particular some elliptic curves, or free surfaces, or some calabi-yau manifolds. Okay, so basically some questions that we have to address is, first of all, if we have some Feynman integral, how do we associate the geometry to this? And also here we've seen already some ways to do this now. We've seen many of these parametric representations. And so now what's going to be the focus of this talk is to not do this parametric representation, but to construct some geometry directly in a space that's more physically motivated, which is this momentum twistor space. And then also, okay, when we have some geometry, of course, we would like to analyze it a little bit. So that's also what we're going to do. Okay, so basically the plan is there will be a brief introduction, and then I will focus on this particular class of integrals, these train track integrals. So these are basically generalized box integrals. And the main results are going to be that for the two-loop integral, we're going to construct an elliptic curve. And this curve will arise at the intersection of two quadrics in a three-dimensional projective space. And for three loops, we're going to construct some surface, and this surface will be some fourfold cover of product of projective lines. And then I will say a bit more about higher loops, how we can always get some calabi-yau as a complete intersection there. Okay, and then I will conclude and give some further directions. Okay, so let's begin. So first, I'm going to review briefly how we can find a geometry for a Feynman integral. So again, what we imagine is we have some Feynman diagram, and we just apply the Feynman rules that we know for theory, and we get some nice integrand. So we can also get this integrand maybe in some other way, but we imagine we have some nice integrand, and then we have a bunch of loop integrations that we have to do. So what we can now do is we can just apply the textbook procedure. So we can introduce some Feynman parameters, and we can start to integrate. So integrate, it means, okay, we're going to try to express this in terms of functions that we know, which would be these polylogs. And this can go well for a number of times, and then at some point, maybe the process is going to stop. And we're going to end up with something where we have a bunch of polylogs, and then it's going to be multiplied by some nice form that will live on some geometric object. So it will live on some variety. So the most, the easiest example is, okay, I introduce Feynman parameters, I do a number of integrations, and then what I'm left with is still some integration to do, but in my denominator, there's going to be the square root of some cubic polynomial. So now clearly it doesn't fall into this class of polylogarithms anymore. So what I would conclude is that there's an elliptic curve that will be defined by this equation here. Okay, so that's how we can do this direct integration method. That's the one way to do this. And then we can also kind of take a shortcut here, because we can say maybe we don't really care about all these polylogs, but if we just want the geometry, we can also get this form by taking residues. So that's the second approach here. So basically, we can again start with this integrand that we have, and we imagine it's a product of some propagators. So there are some poles. So we can start to take residues around the poles. And again, this works a number of times, but then at some point the process will stop because we cannot take any further residues. And then we land on this residue of the highest codimension, and which is going to be this leading singularity. And typically, if this leading singularity just consists of some constant, well, like in a sense, yeah, of some constant, then I would conclude that the integral is probably going to be polylogarithmic. So in the following now, we're always going to look at this leading singularity, and we're going to analyze it. So we will always be interested in taking residues, essentially. But okay, so we don't want to do this by introducing some parameters, but we want to do this in terms of momentum twistors, as I said already earlier. So I will just briefly remind of this, how this works with momentum twistors. So again, we imagine we have some Feynman diagram, and of course there are some momenta, some external momenta sticking out. So now we can repackage basically all this information in some nicer variables. So we can first of all switch to the dual coordinates. So they're just written here. And then we can also go further, and we can introduce these momentum twistors. So they were then introduced by Andrew Hodges. So so the momentum twistors, they're just some points in a three-dimensional projective space. And then what one can work out is how all the objects that we talk about in momentum space are mapped to momentum twistor space. So in particular, if we have some point, so it could be one of those external points or one of these internal points, it's going to correspond to a line in the three-dimensional projective space. So yeah, so there's going to be a line that corresponds to a point. And then also this distance of 2 points, so x minus y squared, it just becomes the 4 bracket in P3. So we just take the 4×4 determinant of those 4 points. So now what I said is, okay, we want to take residues. So in particular, since in this dual space, the propagators, they are essentially just the distance between these 2 points. We will always be interested in this case when the separation between these 2 points is 0, so when they are lightly separated. And then geometrically, what happens there is that these 2 lines, they meet in a point. So that's what we're going to need now all the time. And yeah, okay, also I forgot to say something. Of course, these dual coordinates, they're nice for various other reasons also, because if we imagine that we do this analysis for some amplitude and n equals 4, then they expose also this dual conformal symmetry. So we can also imagine that on this axis, we actually have some conformal group acting maybe. And yeah, then these conformal transformations, they just become the coordinate transformations in this P3. Okay, so now, as I said, we want to apply this dictionary here over and over again to analyze this leading singularity. So the easiest example will actually be this box integral. So this was already done by Andrew Hodges. So here this is the box integral. So so for now and also in the following the graphs in black, they're going to be some graph, some Feynman diagram in momentum space, and then behind it is drawn the dual graph. So and also the integral is written up here. So massive, I mean that the corners here are going to be massive. And now I want to apply this dictionary. So I have 4 external points, 1, 2, 3, 4. So if I want to draw the picture, what this corresponds to in this P3, then I should draw 4 lines. So I should have 4 lines, and they are supposed to be skew because these corners are massive. So for example, we have x1 minus x2 squared is not equal to 0. So they're going to be skew. So this all just also follows from this dictionary. Okay, now I should find also a line that corresponds to this point in the middle here. But since I'm interested in this leading singularity, I should demand that this point is likely separated from all the other points. So geometrically, I should find a line that intersects all these other lines, right? Okay. Okay, so now, as I said, this analysis, it was done by Andrew Hodges, and you can find that to this problem of putting the lines in this way, they are basically, there are 2 solutions that are characterized by some cross ratios. And the point here is, okay, so we get these 2 solutions for this problem. So in the end, what we conclude here is that there are exactly 2 configurations where all these dual points are going to be likely separated. So what we conclude here in the end is that this leading singularity space that we're interested in, so in this case, it would just be 2 points, right? So here it's not so interesting really, but of course now then when we go to now the more complicated examples, it's useful to remember that that's kind of what we're after. Okay, so now we can look at these more complicated integrals, these train track integrals. So as I already mentioned, these are basically a bunch of box integrals that are next to each other. So again, that's drawn here now. And in particular, they were studied by these people in 2018 a lot. What they did was they used this method that I said earlier. They used this direct integration approach. So they introduced some Feynman parameters for some nice conformal integrand, and they started to integrate in terms of polylogarithms. And then they found, in the end, they couldn't continue doing more integrations, and they concluded that the geometry that's associated here to this integral would be given by some hypersurface in a weighted projective space. And to be more concrete, in the case of 2 loops, they found an elliptic curve. For 3 loops, they found a K-free surface, and for 4 loops, they had some calabi-yau freefold. Okay, so now the first thing that we have to do is we want to look at this 2-loop case here and also find the elliptic curve. But again, we don't want to do any integrations, and we also don't want to do this these Feynman parameters. But instead, we just want to apply the dictionary and kind of do the analogy similarly to how this works for the massive box. Okay, so that's what we're going to do now. And so here I'm just drawing 1/2 of the integral for now. Well, 1/2 of the diagram really. So you should imagine there's going to be another box here to the right of it. And now we're going to just start putting the data in P3. So we have these 3 points, x1, 2, 3. So we should have 3 lines, 1, 2, 3. These are the red lines over here. Oh, P3. These are the red lines over here. So, and they're skew. They're going to be skew because again, these corners are supposed to be massive. And so now the first result that we can use is that when we have 3 skew lines, then they determine a quadric in P3. So that's this blue space here, and you can also give the equation. So the equation is written here. And now we can invoke also some fact about quadrics. So a quadric, it's a ruled surface, so we can find different families of lines on this quadric. And if we take some lines that come from the same ruling, then they're going to be skew. So these would be these red lines, for instance. And if I take two lines from different rulings, then they're going to intersect. So that's convenient because, again, we still have to find a line that corresponds to this loop point here. But since we're interested in the leading singularity, this point should be lightly separated. So the corresponding line should intersect all the other lines. But so it means we can just take it to be from the other ruling. So this gives us a way to say where this green line should come from. Okay, so that's how we first for one half of this integral or one half of this diagram really reconstruct the quadric. Okay, so now we want this two-loop diagram, and so now we have to do this twice. So we get two quadrics. So again, for this half of the diagram, that's going to be quadric, and there's going to be another quadric for this half over here. So we get two quadrics, this QL and QR. And now we just have to take care of one final constraint, because we should also, for the leading singularity, ensure that these 2 points here are the two loop points are lightly separated. And so this can be done by demanding that these quadrics intersect. So that's shown here in this picture. And again, so now we have already constructed the elliptic curve, because it turns out that if we have two quadrics in P3, then the intersection is an elliptic curve. So that's how this elliptic curve can arise here. So we just built two quadrics, they have to intersect, and the elliptic curve is there. And we didn't have to introduce any parameters or Feynman parameters. Okay. So now we should also analyze a bit this curve. So maybe we want to have some form on this curve to be able to integrate. So the way this can be done is we can start with the form that we know in P3, the normal form in P3, and then we can take residues with respect to this quadric. And one can easily check that has the right rescaling weight and all that. Okay, so another thing that we are interested in is we want to characterize this elliptic curve, and we know for when we have an elliptic curve, there's only going to be one modulus. So this is this famous J invariant. And so what we can do here is we can compute the J invariant. So here I'm just giving the formula for the J invariant that we have. So this is the formula, and this Z here is some cross ratio. And I'm not writing how it explicitly depends on these quadrics, QL and QR, because yeah, it would take too much time to write it now. But the point is that, okay, we can basically fix some external data. So we can fix some momentum twistors, and we can compute these quadrics, and then we can compute this Z, and we can compute the J invariant. So it can all be made very explicit. So yeah, we can compute it basically. And okay, so why is it useful to compute this? Because also it allows us now to compare. So this integral that I said, this double box integral, it was analyzed many times before, and in particular also it was particularly also analyzed in this paper, where again people did this direct integration approach using Feynman parameters. So they had some nice rational integrand and did a bunch of integrations, and in the end they had something that was dx over square root of a degree 4 polynomial times some polylogs. And they defined some elliptic curve in this way by this equation here. And for this, you could also compute some J invariant. And so now here we did something quite different in the sense that, okay, we didn't introduce any Feynman parameters, and we didn't do any integrations, but we just, okay, did this elliptic curve, it just arose as the intersection of these two quadrics. And we also have a formula for the J invariant, and we can compare the two, and they are the same. So that's the first result, basically, that we find that these two descriptions, they match here. Okay, and that's of course very nice, because I guess if we want to talk about the geometry of some Feynman integral, it should, I guess it should, the best thing would be if it doesn't really depend on how we parameterize the integral. Okay, so that's the elliptic curve, or this double box integral. So now we can start to add more loops to the picture here. So okay, so first now we again want to look at the leading singularity of this 3-loop integral, and we want to construct this in momentum twistor space. So first we can of course recycle what we already know, because we know that if we have one of those boxes here at the end, we're going to get a quadric. So there's going to be these 2 quadrics. So there's one quadric here for this piece on the left, and there's going to be a quadric here on the right. And now we just have to take care of all this data here in the middle. So the way this can be done is, again, to this x1 and this x2, we should put a line each. So we're going to have a line here and another line here. And now we have to also find a line that corresponds to this loop point here, this point in the middle. But again, since we're looking at the leading singularity, the point should also be light separated from the red point. So the line should intersect. So it should cut through these red lines. So we can take actually a point here on each of these lines and say that we just parameterize the line in the middle in this way. So, okay, now I've drawn it a bit badly, but it should go through these points, of course. Okay, yeah, so here's the picture. It's drawn much more nicely. So again, we have a quadric coming from the end. We have these lines L1 and L2 that correspond to the external points. And we have this green line that corresponds to the middle loop point. Okay, and now we can, at this point, we can actually invoke Bézout's theorem. So now we can say, okay, this line, this green line, since we're assuming that everything is in completely general position, maybe something I should have mentioned also, we're assuming that everything is in completely general position. We can assume that this line, this green line, is going to intersect each of the quadrics in 2 points. So that's very nice, because then it means that also this last constraint that for instance, this point and this point are going to be light separated, it can also be fulfilled. And in particular, it can be fulfilled for any choice of these points P1 and P2. So that's actually the next point. So now at this point, we just basically put all the data in P3, and now we have to see that what I'm saying is that this leading singularity locus, it's a 2-dimensional space. So that's the first thing we have to see, because I'm claiming there's some surface. Okay, so the way this can be seen is again that we can actually choose freely these points that we use to parameterize the middle line, and we can still satisfy all the constraints that all the points are light separated. And this is just because, as I said, by Bézout's theorem, the middle line will always intersect the quadric in 2 points. So it's definitely going to be a 2-dimensional space. And then we can say a bit more, because, okay, so let's say we have fixed these points, P1 and P2. So we fixed this point and this point on these lines. Then we still have different choices for the intersection points of the quadrics. So, oh, sorry, I went in the wrong direction. Sorry, yeah. So I don't know, I can, for example, choose this one and this one, or I can choose again this one and here the other one. So in total, there are 4 choices for these intersection points. So in total, we can say actually we have a 4-fold cover of P1 times P1. And yeah, these P1s, they correspond exactly to these lines here. Okay, so in total, we have this 4-fold cover of P1 times P1. And it's also, okay, so the situation is kind of similar for how you can also have an elliptic curve in the plane. So the way we can have an elliptic curve in the plane is, okay, we take some P1 and we take 4 points and we fix them to 0, 1, infinity, 3 of them. And then we just have this last one left, this lambda. And then we can write an elliptic curve in this way. And this curve is a double cover of P1 branched over 4 points. So here again, the situation is kind of similar, except that we don't have a curve branched over some points, but we have a surface branched over some curves. So what we should do now is we should look at what are these branch curves. we should look at basically the analog of these points in the case of the elliptic curve. Okay, so the way this is done is we have to remember what was the reason for why we had different branches in the first place. And that was, of course, because we had different choices for the intersection points. So again, we had these quadrics, and the green line was going somewhere here, and there were different choices for the intersection points here. But now, of course, if the line maybe becomes tangent to the quadric, then there's going to be less branches. So in particular, let's say it's tangent towards this, towards well on the left quadric, then there are only going to be two choices left here. And so we can compute when does this happen. So and we get these two equations. So for example, if the first equation is fulfilled, then this green line is going to be tangent on this QL, and if the second one is fulfilled, it's going to be tangent on this QR. Okay, so in total we get these two curves, this delta L and delta R, and we can also see, since these are quadrics, they are by degree 2, 2, and they live in P1 times P1. So from this we can conclude that they're actually themselves elliptic curves, and yeah, also okay, the second point I already said here, because as I said, if we are on one curve but not on the other, then there's still two branches left. But then there's also the situation where they intersect, and it turns out they intersect in 8 points, and there we only have one branch of the surface. Okay, so this is also summarized here in this table. So again, if we're on the intersection of these two curves, then there's going to be one branch. If we are just on one curve, then there are two branches, and yeah, in the rest of the space we have 4 branches. Okay, and so we can use this information to compute also the Euler characteristic of this surface. So it can be done using the surgery property of the Euler characteristic. So one has to use, for example, also here it also enters that these curves, they are themselves elliptic curves, so the Euler characteristic is 0. And indeed, for this K-free surface, we get that the Euler characteristic is 24. So so this is also expected, of course, because yeah, so we know that the Hodge numbers for the K-free, they look like this. So this Hodge diamond looks like this, and this Euler characteristic is just the alternating sum of this Betti number. So it should be 24. Okay, so that's correct. And yeah, so here we just computed it directly. Okay, so a few more things we could do is we can look at the dimension of the modular space here. So this can be done by basically counting parameters. So essentially, in this case, you kind of have to take these two curves, delta L, delta R, and you have to count, okay, how many curves are there basically that intersect in 8 points. And we find that the dimension of the modular space here is 11. And now for K-free, this is nice because we know that this is also related to the pK number of this K-free surface, because they should add up, well, sorry, so the pK number and the dimension of the modular space, they should add up to 20. So in this case, we should get that the pK number is 9. We can also write a holomorphic form like one does for the elliptic curve, basically. It's just written here. And one more thing we could look at is some kind of symmetries of this construction. So we can look at some involutions of this K-free surface. So in particular, we look at these Niculian involutions. So these are some involutions that basically don't change the holomorphic form. And then there are some nice theorems by Niculian that tell you that if you know something about the number of fixed points of this involution, then it gives you bound on the pK number. So in our case, we found such an involution. So yeah, we found such an involution, and it turned out to have 8 fixed points. And then we could look up in these old papers that the pK number has to be greater or equal to 9. So it's actually perfectly consistent with the analysis also that we did here, and it seems like this bound is satisfied. Okay, so that's for the K-free, and so now there's an important open question. So Right, so for the elliptic case, we could just easily compute the J invariant, and then we could compare it to this construction that people did in the to this hypersurface in weighted projective space. So now we would like to do this here, but we don't really know how to do this at the moment. At least I don't know how to compare if this is now the same K3 surface or not. That's something that would be interesting. Okay, so now we can again add more loops to the pictures, and now I'll be a bit brief. So again, we have two quadrics, obviously, that we already know. We get this from the boxes here at the end, and now we take care of all the data in the middle. So we have to these dual points, we put these lines L1 and L2 and L3 and 4 and so on. And again, we put the green lines corresponding to these points here in the loop. And then, okay, at this point, we just have to also impose one more constraint, namely that these 2 points are lightly separated. So there's a constraint here, and that amounts to imposing another constraint in P3, namely that these green lines, they intersect here in a point. And again, you can see that this is going to be 3-dimensional space because there are these 4 lines, and basically impose one more extra constraint. And yeah, it's also okay. At this point, you can also see that this is going to generalize. So you can iterate this procedure now. You can keep adding these lines and demand some intersection. And so in total, we can actually always build for these train track integrals here. Now we can always build this calabi-yau manifold as a complete intersection that could be embedded in some toric variety. So the usefulness of this is maybe that you can use some combinatorial description. That's in particular this Baturas-Borisov construction of calabi-yaus to compute some data about them. So you can compute some Hodge numbers, for instance. And for this picture that I showed now, so for the for loop diagram that's supposed to be calabi-yau threefold, we did it. So we computed some numbers and the Euler characteristic with this computer program Pulp. The problem is that, okay, to actually compute something here, it also actually quickly becomes kind of impossible because the combinatorics they also grow quite badly. So in particular, this is because the co-dimension in this embedding space here. So in this embedding space, it grows also with the number of loops. So in other words, we have many constraints that we impose. But the message is that for this general train track integral with L loops, we can always build calabi-yau L-1 fold. And the embedding space would have a dimension of 2L-1. So you can actually see that the codimension also is L-1. Okay, so yes. Okay, so that's okay, I'm doing fine with time. Okay, so then I'm already going to conclude here. So okay, so what did we do here now? So we looked at this leading singularity of the train track integrals, but we did this in momentum twistor space. So not by looking at Feynman parameters. So so what we saw is that okay, for the 2 loop, for this double box integral, we could get the elliptic curve as an intersection of 2 quadrics in P3. For 3 loops, we had this 4-fold cover of this P1 times P1, and when we go to higher loops, we could see that we can add. We always have to add more equations, or we add more space and we add more equations in some sense. So, but just from how the equations scale, we can see that there's always going to be a calabi-yau in there. Okay, so why was it nice to do this in momentum twistor space, or what was the usefulness of not introducing these Feynman parameters? So one point is that okay, really all we ever have to deal with is kind of intersection of lines. So that's nice maybe then because well, I guess linear equations are a bit easier than quadratic equations, but of course it comes at the cost of having to impose many of them. Another nice feature is that we don't introduce any unphysical parameters. So we construct this geometry directly in a space that has, of course, also relevance in scattering amplitudes in general. So that's another nice feature of this. And finally, as I said, this in particular also in relation to amplitudes in n equals 4, that this conformal symmetry becomes manifest. Okay, so now first thing, so now some further things that can be done here. So first of all, one can supersymmetrize this construction. So Christian here suggested this, that yeah, one can supersymmetrize this whole construction. So basically the idea is that when you look at the amplitudes in n equals 4 superangles, then they're not only conformal, but they're actually going to be superconformal. And so if we analyze this leading singularity, maybe it's something that can even be respected there. And the way this can be done is you can basically do the whole analysis that we did again, but you formulate all these intersections that we have, all these intersections of the lines. You would formulate them in terms of some delta functions, and that are going to be nicely invariant. And then at the end, it's very easy to supersymmetrize because you would just replace P3 by P3/4, and the delta functions by some supersymmetric version. So that's one thing that can be done here and can also be, I guess, explored a bit further. So another thing is that we can also build more complicated diagrams. So for instance, we can build kind of like a fishnet type thing. So we can build like a grid of boxes. I'm saying fishnet type because of course there are more external points here. It's not just a 4-point, but there are many external points here. But then just from how this scales with the equations, we can also see that there's going to be some calabi-yau involved in there. And maybe another thing that can be done is to look at also massive internal propagators. Okay, so there's still a bunch of open questions. So one thing is definitely the generations of this. So because again, so if we have this such a train track integral, and we start to remove some of these legs, some of these external legs. So in other words, we're kind of collapsing we're making some of these dual points collide. Then at some point we're gonna see some ladder diagrams, and they have been computed a long time ago, and in particular in terms of polylogarithms. So at some point, what we should see is how this geometry degenerates to something much simpler. So and that should also work for these fishnet type diagrams, because they are eventually, if we start to remove external legs or dual points, we should find these Buster-Dixon integrals. Yeah, these fishnet integrals. Okay, so another open point is, okay, how are we going to deal with non-planar integrals? Because yeah, so now this was all done use this Twistor approach, so it's tied to planarity, but I guess it would be nice to also have a description for non-planar integrals, because we also know that there's going to be some calabi-yau for non-planar integrals. And then, okay, another point is the role of different parameterization. So now for this, okay, so we had this one example now for this double box integral, where we did this construction in Twistor space, and we could actually compare it to Feynman parameter way to get a geometry to this direct integration method, and it turned out to be the exact same elliptic curve. But okay, we also know that there are other representations of the integrals. So in particular, something that has come up a lot now in this week has been the Bykov representation. So and in general, we have to make sure that we get the same geometry there. And there are, of course, also examples where, in particular, this paper from last year, where people use different representations and they actually find different elliptic curves. So in this case, in this paper that I'm mentioning here, it's for the sunrise intervals, but of course, it would also be good maybe to see what happens in this for this double box integral. Yeah. Okay, and then another point is, one thing we haven't really used here is this calabi-yau mirror symmetry. So this has also appeared in the analysis that people do to describe some calabi-yau geometry that's associated to Feynman integrals. There have been various papers also here, and yeah, I guess maybe, I don't know, maybe even the next talk, I don't know, might also involve that, I don't know. Okay, yeah, so that's actually the end, and thank you. Yep.
All right, let's all take a moment to unmute ourselves to thank Matthias with a round of applause. And it looks like David has the first question.
Thank you, Matthias, for this wonderful talk. At every stage along your interesting journey, I saw the precise parallels with the multi-loop sunrise diagrams that I've been talking about. I mean, I saw elliptic curves, I saw the K3 surface, which I didn't talk about in my talk because it's already 15 years old, that comes from the 3-loop sunrise diagram, and I saw calabi-yau threefolds. You gave wonderfully explicit formula for your J invariant, just as I did, which is dependent upon Z, which is determined by some external kinematics. So the thing to look at is exceptional values, not singular values, not of the differential equation, but the exceptional values that I was talking about, where the problem becomes modular. And you can do that. You can look at your J invariant of Z and ask yourself, is there some particular kinematics in which your Picard-Fuchs operator, gives you smaller characteristic numbers? Not just look at the singular places, but regular places. So go to your J invariant, find some elliptic curve which is an elliptic curve over some Q, over Q, or as I was doing with algebraic numbers, and then go back and look at your Hodge numbers, look at them, and you'll find that you're at what Duco von Straten, who taught me this in Mainz 10 years ago, he calls them singular values. He calls them singular because they're remarkable, they're special, So you have down there, you take every slide of your talk and go back for your train tracks and your ladders and go back and look at my little toy example of sunrise diagrams, and then ask yourself, what are the special points? What are the places at which all your blow-ups and all the algebraic geometry you're doing becomes very, very special, very different?
Okay, I will go back and take a look. That's a really nice suggestion. Thank you. Thanks.
We also have a question from Karen.
Hi, I just wanted to ask, let's see if this will work for me to annotate on your screen. You had your fishnets. Okay. What if you take your fishnets and join them up this way? What do you know about those guys?
Well, so then it's not a planar diagram, right? So
no, it's not, but it's still got a lot of the same properties, right? Because it's almost planar in the sense that if you ignore the external edges, it's planar. So in the pure graph theory sense, it's planar, but with the distinguished vertices on two different faces instead of on one.
Okay, I can't say immediately what happens, but so do you have a suspicion, or do you
I know a tiny bit about C2. That's all. So I'm not as far as having a suspicion for you.
So for C2, you mean they're the same, or?
The C2 at 2 is 0, but then the C2 at other values is probably not.
Okay. Okay, I can't say right now because it doesn't look planar, so I have to think a bit harder, I think. But it's okay. It's a good suggestion. I think I will look at it. Thank you.
We also have a question from Lance.
Hey, nice talk, Matthias. Just a quick comment on that last figure. That's reminiscent of some work that Benjamin Basso did with DeLeong Li in trying to make the fishnet graphs that we looked at more periodic. But he probably didn't do it in a graph by graph. But they may have looked at it a little different way. But if you're interested in that case, you might look at Basso and Li.
So you're talking about the graph that Karen drew, or?
That's right. Yeah.
Okay. Okay.
And I also wanted to.
Thanks.
Yeah, I don't know if you'll find it anything useful in there or not, but it's one place to start. Another comment is just that, yeah, I think it's very interesting to look at these degenerations to polylogarithmic, because when it comes time to actually get numbers out of these integrals, you're going to have some differential equations, and you're going to need to fix them with boundary conditions. And this seems like a nice surface, these surfaces where the things degenerate to polylogarithmic seem like good places to fix the boundary conditions.
Yeah, indeed.
Yeah. And then a question was, have you thought about Yangian symmetry at all? Because a lot of these integrals, people have been exploring Yangian symmetry and differential operators that come from that. And can you see any of that from your side?
Okay, so I haven't thought so much about it, but I know that I think some of the other people in Copenhagen were thinking a bit about this, and I know I'm afraid I can't be more specific because I haven't thought about it so carefully myself. But I don't know, maybe Christian knows more, or also Matthias. I'm not sure. I'm sure some people mentioned this before. But yeah, I guess we can also look at this.
Okay, thanks a lot.
We also have a question from Laura.
Hi, very nice talk. I have what's probably an ignorant question, but I was curious. You mentioned calabi-yau involutions, Nikulin involutions in the K3 case. Mm-hmm. Is there any significance to discrete automorphisms of calabi-yaus for, say, calabi-yau threefolds or the higher dimensional ones?
Okay, so I'm sure there's something you can do, because, okay, so this construction that we do, there are definitely some symmetries to it. So, but we haven't really worked this out. So, but okay, now that I think about it, I guess, so for the Nikulin involution, for instance, for the K3 case, it corresponded to switching these intersection points. So that's something, I guess, in principle, you can also do for the higher dimensional cases. Mm. But yeah, I don't know, maybe it could be interesting to work this out. I'm not quite sure at the moment.
The origin of my question is, a lot of these symmetries have been classified for, say, calabi-yau threefolds, so I didn't know that.
Okay.
If they're actually available, then you could ask what their significance was.
Okay, that's a nice hint. I wasn't aware of this, but yeah, thank you. That's helpful, actually. Yeah. Thanks.
And then we have one final question again from David, who is muted at the moment. David.
There are so many sparks flying in my mind at present. You know, Lance has talked about fishnets, we talked about train tracks. Now, I'd forgotten that I'd done that work. You know, thank you very much for reminding me that in 1993, Andrei Davidichev and I did. But what Andrei and I did later, and it took us 10 years to do it, is we sum those massless off-shell ladder diagrams to all orders, and Andrew and Lance and the co-workers have done that for other diagrams. So we have a non-perturbative answer down there, and it's very, very simple, you know. I mean, so there's something here that you know, you should be maybe, hopefully it won't take you the 10 years that it took Andrea and I to do it for all cross ratios, and because Andrew and Lance and co mopped up quite quickly. There's something down there. Okay, we're only looking at a tiny subset of Feynman diagrams down there, but we're making contact with the non-perturbative physics of people like Benjamin Basso, you know, deeply informed what Lance has been doing. And at the end of the day, the final results to all orders and the coupling constants, you know, when we have planar diagrams and the finite circle of convergence and all of the toy physics of n equals 4 super Yang-Mills. So, you know, look at these, look at this as a gem mine. Try and go to all orders. Might take you less than 10 years.
Okay, I guess thanks for the encouragement. Maybe, yeah, it would definitely be really cool to get some non-perturbative answers here. Okay. Thanks, yeah.
All right, great. Well, those are some great questions. now I guess we can thank Matthias again. And so next we have Chuck Doran telling us about the calabi-yau geometry of Feynman integrals. And Chuck, we can't currently see you, although we can see your screen.
Okay.
Oh, there you are.
That?
Perfect. Go ahead.
Okay. Great. Okay. So, well, again, I didn't have time to raise my hand for Matthias's talk, but that was a great talk. I think you'll see a lot of resonance between some of the questions Matthias was asking and hopefully some of the answers I have to give today in a few examples that I will illustrate. Okay, so the title of my talk is the calabi-yau geometry of Feynman integrals. Okay, so that was actually what I was asked to speak on by the organizers. And although aspects of this are going to be survey-ish and they're covering sort of a lightning review of calabi-yau geometry and moduli, the heart of the talk in terms of answering these questions is based on joint work with Andrei Novoseltsev and Pierre Van Hove. And Pierre is with his kids right now, so he couldn't make the talk. All right, so what is the connection to the calabi-yau geometry and Feynman integrals? Well, we've certainly been seeing examples of it in the last talk, and I gather other talks in the workshop. But I would say that the starting point for thinking about this mathematically, and again, I am a mathematician by training and a geometer, in fact, is you start with Feynman graph, okay? And physicists have this marvelous way of attaching to Feynman graphs Feynman integrals. Okay, and there's all sorts of conditions that one should be saying here about dimensions and propagators and what have you. Oops, INT, okay. But where the geometry comes in is in passing from the Feynman graph to the Feynman graph hypersurfaces. So think second Zemansic or first and second if you like. So Feynman graph hypersurfaces. Now as a geometer, you might say, hey, this is marvelous. Okay, we have a hypersurface. The problem is these hypersurfaces are incredibly singular. Okay, they're singular in codimension that can be problematic for a lot of analysis. On the other hand, we have a very reassuring result by Bloch and No and Kreimer, which tells us that the underlying motive of the Feynman graph hypersurface is going to reproduce the Feynman integral. Okay, so it's going to give us what we want. On the other hand, this dashed arrow is not really effective. There's no procedure, universal procedure to follow that's effective to produce the integrals and do computations using this. So, inspired by a number of examples, including these multi-loop sunsets that David was talking about, we're taking a different approach. And the different approach is to associate the Feynman graph hypersurfaces, what we'll call Motivic calabi-yau manifolds. Okay. And you've seen examples of this. You know, you derive an elliptic curve associated to these the Feynman graphs, the Feynman integrals that actually has its periods capture the inhomogeneous differential equation satisfied by the Feynman integral. More precisely, you'd want to capture the full motive that Bloch and No and Kreimer are talking about when they talk about the Feynman graph hypersurface motive. But you're still dealing with geometry, so how do you get from there to the integrals? Well, you do it in two stages. You first pass to the Picard-Fuchs differential equations. So this would be step A, this is step B, and then from there, using various techniques, some computational, some theoretical, you pass to the Feynman integrals. Okay. So this is the rough picture. And of course, in order to get any real information in general about what the calabi-yau geometry of Feynman integrals should be, your starting point has to be where the geometry lives here. In other words, the Feynman graph hypersurfaces. And really, we're talking about cases to derive information about the general situation, cases where we understand the A, B, and the C. Okay, so if we don't understand the A, B, and the C, I don't know how to effectively realize this correspondence. So today, I want to take 3 cases. And I don't mean individual graphs, I mean 3 infinite families or towers, if you like, of Feynman graphs where we, and by that I mean with Novoselic and Van Hove, understand A, B, and C. Okay, so that's the rough idea. And as I said, since I'm a geometer and this was my purview, the focus today is on the geometry. Now, that's not to say that Picard-Fuchs differential equations are not important. They're absolutely central to the subject. It's just that I quite conveniently, for the purposes of passing from geometry to Picard-Fuchs differential equations, can refer you to my MSRI mini course running over 5 weeks, starting October 27th. So you'll have more than enough of me talking about the relationship between geometry and Picard-Fuchs differential equations. I believe the way they're setting it up is that members of the special semester will be live when I give the course, and then the lectures will be recorded, and so anyone can watch those. And then there will be discussion sections once a week that'll be open to everyone. So it sounds like a great opportunity for this community, this physics community interested in amplitudes, to interface with that. Okay, having said that, everything I'm talking about is backed up. The back end involves heavy computation with Picard-Fuchs differential equations to justify that the calabi-yaus we're dealing with are motivic and to explore their geometric properties. Okay, so I want to address today a couple of big questions. Okay, now these are big questions from the standpoint, at a minimum, of a mathematician looking at the subject. I've been messing around with geometry of this sort, Picard-Fuchs differential equations, for, I don't know, 20 years, 30 years, I don't know how long I've been doing it. Yeah, 30 years. Anyway, so that's where I'm coming from. On the other hand, so the questions I'm after are questions about the fundamental relationship or potential fundamental relationship between calabi-yau geometry and this kind of physics, Feynman graphs, okay? So the first question would be, how does the correspondence Feynman graphs Motivic calabi-yau manifolds work? Okay. And then a second is, well, okay, you've passed from this problem involving Feynman graphs and Feynman integration to a problem involving geometry. And it's a well-studied subject. As I said, I've been working in it for 20, 30 years. So the question is, how are the key features of calabi-yau geometry and moduli reflected in, well, okay. It's one thing to talk about a single Feynman diagram, a single Feynman graph giving rise to a calabi-yau. And maybe you throw some parameters in and you get a family of calabi-yaus. But it's another to say, if the whole theory of Feynman graphs and Feynman integrals is supposed to be copied over, to have some geometric avatar through these motivic calabi-yaus, you should be able to say something about passing between Feynman graphs. in the context of calabi-yau geometry and moduli. So in the relationships among Feynman integrals. Okay, so we're going to start with what I'll call a primer on calabi-yau manifolds, with a focus on dimensions 1, 2, and 3. Okay, there'll be a bit of overlap with the exposition from the last talk, but hopefully that'll just make it easier to understand. Then we'll look at the three families, sort of towers of graphs and their associated Motivic calabi-yaus. Okay, so, oh, and let me apologize in advance. I'm not going to be giving references to the literature in any real way. The mathematics of the examples I'm talking about in many cases goes back hundreds of years. So in the paper we're writing, I'll include citations to the literature and all of this. The physics, of course, is more recent, and I'll do my best to include those in the paper. But for now, don't expect to see a lot of citations. So primer on calabi-yau manifolds and moduli. So we'll start with the first case of elliptic curves. It's true that in fact there is a even simpler case of dimension 0 calabi-yaus. So a dimension 0 calabi-yau is in a rigorous way a pair of points. Okay. Having said that, I won't be dwelling on that here. Okay, but it's good to bear in mind when I talk later about fibrations. So elliptic curves, well, we're used to considering so-called normal forms for elliptic curves. So what are they? Well, for instance, there's the Hesse normal form. So it's x cubed plus y cubed plus z cubed plus mu x, y, z equals 0. There's an example. Okay. In particular, the Hesse normal form represents an elliptic curve as a cubic in CP2. We have the so-called Legendre normal form. I'll write it again as a cubic in CP2 just for consistency's sake, but usually you write an affine version of this equation. So it's y squared z minus x times x minus z times x minus t times z equals 0. Now notice each of these has a parameter that moves, so mu in this case, t in this case. They both have the property that every elliptic curve over C, every smooth elliptic curve over C, has a realization for at least one mu or t value in the family. On the other hand, the fact that they come as families means that as a family, they contain extra information. In the case of the Hesse pencil, it has to do with Mark III torsion, okay, gamma naught of 3 structure. In the case of the Legendre family, Mark II torsion, full Mark II torsion, gamma of 2 structure. You also have the Weierstrass normal form. So y squared z minus 4x cubed, I think I have the signs right, plus g2x z squared plus g3 z cubed equals 0. Where now you have redundant parameterization. Well, okay, it looks redundant because we say this is a one parameter family of elliptic curves, but really if you think of g2 and g3 as a pair of coordinates on a weighted P1, okay, you discover that this is a natural realization of the J line, okay? You of course have to give the J invariant, which is G2 cubed over delta, which is G2 cubed minus 27G3 squared. The usual story, but at the end of the day, the advantage of using the Weierstrass sort of over parameterization is that you get all the charts on the J line naturally. Okay, and what then are the moduli spaces of elliptic curves? Well, they're nothing but what are known as modular curves. And the reason I'm emphasizing modular curves as opposed to just the J line is because when you take these different normal forms, there's extra structure. Okay, there's extra structure of marked points and marked torsion, what have you. And you get this beautiful panoply of modular curves that are studied in number theory. All right, what happens when we pass to K3 surfaces? Well, for K3 surfaces, again, you can ask for normal forms. And let's start. Let's start by writing down some examples, okay? So we said that the Hesse pencil came from looking at cubics in CP2. Well, we can look at quartics in CP3. So quartics in P3. Okay, that's fine, I can do that. That's good, right? I get a 19-dimensional family of quartics in P3 up to automorphisms of projective space. On the other hand, I don't get all K3s. I don't even get all projective algebraic K3s in this way, okay? So what happens is I get all so-called 4 polarized K3s, which is almost tautological. It's the class of K3s that admit a projective realization as a quartic hypersurface in P3, okay? The good news is that there's actually a 20-dimensional period domain, if you like, for K3s, replacing the upper half plane for elliptic curves. And so you have countably many of these 19-dimensional moduli spaces of polarized K3s inside it. So the analog of Legendre now is double covers of P2 branched over, well, a sextic curve. Okay, and these are so-called 2 polarized K3s. But what about the intersection of these loci? Well, in general, when you intersect a polarization of 2n type with 2m type, you're going to get K3s with an enhanced polarization by a larger lattice, a lattice of higher rank. So the analog, if you like, I'll give an analog, the Weierstrass equation would be to consider internal elliptic fibrations with section. And if I do that case, it would be polarization by the lattice H, which is just this lattice 0, 1, 1, 0. Okay. So we're led to the notion of studying moduli spaces that are moduli spaces of lattice polarized K3 surfaces. Very good. So what is the big lattice? The lattice that all these lattices have to live in? Well, this is the middle dimensional integral cohomology lattice of a K3 surface. It's called the K3 lattice. And the K3 lattice, lambda K3, is H plus 3 plus E8, negative definite E8 lattice, 2 copies. Okay. So we've already seen the Hodge diamond. Oops, I have to do it right though. We've already seen the Hodge diamond for K3 surfaces. If I can actually do it, there we go. And you see inside this Hodge diamond for K3 surfaces is this 20 in the H11 part, okay? Now, what's important about studying moduli of K3s or moduli of lattice polarized K3s is that all the algebraic polarization stuff lives in this H11 part. And what's orthogonal to it, the transcendental part, is what has non-trivial integrals of the 2-0 form. Okay, so what that means is that by fixing some sublattice L in the K3 lattice with, say, signature 1 comma rho minus 1, where rho is the Picard rank, so the proposed rank, or the rank that we're going to assign to the algebraic part of H11, we find that the dimension, the complex dimension of the moduli space of L polarized K3s is actually 20 minus rho. This is a result that was alluded to in Matthias's talk. Okay. However, there is now a new phenomenon, okay, that we didn't see in the case of elliptic curves, and that's this notion of rank jumps. So K3 surfaces acquire ADE singularities. Okay, so these rational double point singularities, the natural class of mild singularities for a K3. And when they do that, that ADE lattice gets added to the L lattice. Okay, so in fact, you find that on the loci, I'm sorry, I have to finish the sentence. Along subloci in moduli. Okay, and these subloci and moduli then can naturally be identified with moduli spaces of new K3 surfaces. With higher Picard rank. So higher Picard rank, i.e. lattice polarization. All right, excellent. So we have this new phenomenon for K3s. Now what about calabi-yau threefolds? Okay, so calabi-yau threefolds. Well, again, you can ask for the analog of a normal form. Now, we're not going to delude ourselves, right? In the case of K3s, we did not have a universal K3 surface, class by class, okay? So again, you can ask for normal forms that are the analogs. So here, the analog of the quartix in P3 is going to be quintix in P4. Okay, that's the famous quintic hypersurfaces, or the first examples of calabi-yau threefolds. The analog of the double covers of P2 branched over a smooth sextic curve, and I should add, it doesn't have to be a smooth sextic curve, it could be a pair of cubic curves, for example. Okay, it's something that resonates with the previous talk. The analog there is double covers of P3 branched over, oops, it looks like we lost screen sharing.
Yes, indeed.
Let me try it again. Bring this back. Okay. So screen sharing is lost. Screen mirroring went down. Now I have it back. I'm using something called Reflector Teacher, which I have to use for teaching, and it works pretty well most of the time. Okay. Screen sharing. Screen sharing is on. And yeah, that looks good. Okay, now let me try again. Share screen. Where is it? Yeah, where is it? Okay, let me try something less elegant and see if I can get it to work. Okay. It's supposed to be there. Go to share screen, and it's not visible anywhere.
You want to try disconnecting for a moment and reconnecting, or?
From Zoom?
Yeah.
Okay. Hopefully I can reconnect. Let me try.
Okay. Okay.
Let's see if this mirroring is working now. Okay, I'll reboot Reflector Teacher and see if that fixes it. Okay, do this, screen mirroring. Okay, one more attempt with this, and then we'll try something more drastic. So, share screen. Okay, well, I'm not sure how we lost it. What can we do? So I have a backup plan. I can send you the PDF, and you can advance it.
Or can you bring it up on your own monitor?
Ah, yeah. Send myself the PDF. That's what I should do. Okay. So we'll give up on the iPad, and I say give up on the iPad. Now I see it reflected. Okay, hold on. Let me make one more attempt. Because I see it on the screen right now, and that's okay. I see it on the screen. Zoom.
You can connect to Zoom with your iPad.
Look. I think it's back.
Ah, there we go. We see it.
And we'll keep it as long as we can, and then our backup plan is to do the PDF.
All right.
Okay. Hopefully, I get an extra few minutes for this. So, double covers of P3 branched over an octic surface. Okay. That's the analog of the Legendre family, and that's the analog of the double covers branched over sextics in the K3 case. And then if you want an analog of the fibrations we were talking about earlier, it would be, again, an internal fibration. But now you're three-dimensional. You can fiber in codimension 1 or codimension 2. So it's fibered by K3 surfaces and or elliptic curves. Okay, so these are all special normal forms, if you like, for Calabi-Yau threefolds. No claims that it covers everything, nor that everything will have all these structures. Okay, what about Calabi-Yau threefold moduli? Well, for that, we have the more complicated Hodge diamond. 0H2, 2, 0, 1, H2, 1, H1, 2, 1. 0, oops, 0, H1, 1, 0, and then 1. And I left out a row of zeros. 0, 0, 1. Okay, great. So here's the Hodge diamond for a Calabi-Yau threefold. Now, H21 and H11 are the only Hodge numbers that matter in this context because of just properties of chilarity and whatnot. You get that H21 equals H12 and H11 equals H22. What's really important is the interpretation geometrically for these Hodge numbers. So the dimension over C of the moduli space of complex structures of a Calabi-Yau is a Calabi-Yau threefold is H21. More generally, it'll be Hn minus 1, 1 for a Calabi-Yau n-fold. And since we're talking physics a bit, I'll say the complex dimension of the moduli space of complexified Kähler structures, so the dimension of the Kähler cone, is equal to H11. Okay. What's the new phenomenon now? Well, the new phenomenon is known as topology changing geometric transitions among moduli spaces. Now, the way I'm presenting them here is going to seem very similar to the phenomenon of rank jumps in the K3 case, because I want it to seem that way. But there are many important differences too. But there's two ways to run this. You can degenerate and then resolve singularities. in which case your H21 will go down and your H11 will go up. Or you can do a birational contraction, think blowing down if you like, contraction, and then a smoothing of the resulting singular calabi-yau. In which case your H21 goes up and H11 goes down. And you can combine these. So for example, generic quintics and double octics, those first two normal form types I mentioned in the last page, are related in this way. Okay, great. Now, the other thing you're going to see a lot of in the context of calabi-yau geometry, and we saw a little bit of it last time in the previous talk, and I'm sure shows up in other talks in this workshop, are so-called toric constructions. Now, toric varieties are never calabi-yau unless they're non-compact. Okay, so compact calabi-yaus are not going to be toric varieties. On the other hand, calabi-yau hypersurfaces and complete intersections in toric varieties form a really nice class. You get thousands, millions of examples. Okay. Another possibility, another way of using toric constructions would be to take, say, branched double covers of a toric variety. Okay. The usual context in which this happens is the generic branch double covers. In the context of some calabi-yau examples that Jake was playing with, this led to a realization of the calabi-yau sitting in a weighted projective space, all ones and a two at the end. That's one example of how you could present this. On the other hand, even when you're double covering over projective space, you don't have to work with the sort of generic case. You can go all totally non-generic and do configurations of lines. There's some nice recent work of Osono and Yao and others, and Lien, working out some illustration of this in all dimensions with some modified versions of mirror symmetry for singular calabi-yaus. So this is a rich subject there. And then also calabi-yau fibrations over a toric base is another good example. Now, if you've been paying attention, you will say, actually, the second dot here is actually subsumed in the first dot, because a calabi-yau fibration over a toric base says that generically, for a point in the toric base, the fiber is a calabi-yau manifold. But I told you that a calabi-yau zerofold is a pair of points. So that's a double cover. And where the branching takes place is where the pair of points collide, and there's your singular calabi-yau zerofold, if you like. Okay, but the key for utility for these toric constructions tends to be genericity. So genericity, and that's genericity in the defining equations of the hypersurfaces or complete intersections or what have you. Genericity reduces much of the geometry to combinatorics. Okay, so for example, analysis of polytopes and things like that, reflexive polytopes, the Baturin-Borisov approach to complete intersections. Okay, so the easy case of a Motivic calabi-yau would be to find that Motivic calabi-yau equals a calabi-yau arising from one of these generic toric constructions. Okay. So for example, I could ask in the context of the previous talk, there's a beautiful realization torically as a complete intersection. Is the general mass parameter version a generic complete intersection of that class? Okay. If that's true, then the Hodge number counts that are derived combinatorially that were mentioned would actually reflect the Hodge numbers of those calabi-yaus. If not, you're not getting necessarily the same answer, and much care has to be employed. Okay, so let's talk about our first tower. It's the multi-loop sunset Feynman graphs. So I'll just do a little schematic here. You all know what I'm talking about. Okay, so now the graph hypersurface, and I want all the masses, n of them, I'll say n masses, and I want my p squared. Okay, so I want all the parameters in place. So now the graph hypersurface is itself a singular calabi-yau. And this is the only class of Feynman graphs where the graph hypersurface is literally a singular calabi-yau. Okay, in all other cases, it's going to be some kind of singular fauna. Okay, fine. So this is obviously the starting point when you're looking for a role for Motivic calabi-yaus. Now, having said that, it's a singular calabi-yau. You don't win unless you get smooth calabi-yaus generically. Okay, so theorem, and this is with Novotselt-7 van Hove. Okay, and this is a sampling of results, but these are the ones that are relevant for the talk. So for general mass parameters, the Motivic calabi-yau manifold, and I'm going to just denote it schematically as x n minus 2 to indicate in parentheses its dimension, of the n minus 1 loop sunset graphs are in fact generic, smooth, bipartite, so coming from a pair of equations, complete intersections in toric n-folds. Okay, and all very explicit. Moreover, because of that genericity condition and an enormous amount of care, you can check that the Hodge numbers of x m minus 2, counting respectively the complex and Kähler moduli, are, okay, well, if you keep track of my indices, the relevant Hodge number for the complex structure modulus is h n minus 3, 1, and that's n, okay? And h11 is 2 to the n plus 1 minus 3n minus 4, and these are valid for n greater than or equal to 5. Okay, now I should just comment. This uses, well, first of all, the existing formulas in the literature prior to my work with Novotselt-7, our first paper, were insufficient to address this result, okay? Because there was no closed form expression for these Hodge numbers that was in literature. We gave a closed form expression, but even with that closed form expression for the stringy Hodge numbers, a detailed induction has to be done. And it's a slightly subtle induction. But when you do it, you get this nice result, okay? 3, the x of dimension k are themselves fibered by the x k minus 1 over p1. Well, it's hard to read. Over p1. And of course, you do that iteratively. So that gives you an iterated calabi-yau fibration in all dimensions. Okay. And finally, if you ask for such physically interesting things as thresholds, you see that the thresholds correspond to ordinary double point or conifold collisions. So collision loci. Of the xn minus 2. Okay. So all of that is the best of all possible worlds. Okay, quote Leibniz. All right. What about the next class? Okay, let's do ice cream cone. Feynman graphs. So the ice cream cone graph looks like this. You have your cone, and you have the top of the cone. Okay, and then you have some scoops of ice cream. There we go, and then we have these. So you've got a P1 squared, a P2 squared, and a P3 squared. Conventionally, I usually put the P1 squared here, the P3 squared here, and the P2 squared there. And you have your various masses that you have to worry about. Okay. All right, so theorem, and this came as a surprise to us. The Motivic calabi-yau manifolds y of dimension n minus 2 of the n minus 1 loop, or if you prefer, n minus 2 scoop Feynman graph. So ice cream cone Feynman graphs. ICC graphs are isomorphic. Isomorphic to those of the n minus 1 loop sunset graphs. Okay. Now this was really very much a surprise to us. We didn't know what to expect. There were some hints coming from 2-loop, but in fact we have this result in general. And as a corollary, it answers a rather simple question about the relationship between Feynman graphs and calabi-yau moduli spaces. The map from Feynman graphs to calabi-yau moduli spaces is not injective for calabi-yau manifolds of any dimension. Okay. Now, this might be viewed as troubling, okay, but perhaps it shouldn't. Let me just explain. We're not saying that the families one considers to compute Feynman integrals, say, over, I don't know, P3 squared base or whatever, are going to be the same families. We're saying just like for elliptic curves, where the J line is the source of all elliptic curves and you sample from it, you're sampling from the same family of calabi-yaus in every dimension, as you already figured out with the sunset. Okay? So you can think of it as sort of a statement about the sunsets being reparameterized as a family, and those are the ice cream cones. Okay, but it's natural to ask, is there still some kind of geometric way to distinguish these cases that plays well with calabi-yau geometry? And for that, we bring up mirror symmetry. Okay, so the so-called calabi-yau mirror symmetry takes one calabi-yau, say threefold, and says there's a mirror calabi-yau threefold. And the Hodge diamond flips in a way that exchanges the complex structure Hodge number and the complexified Kähler structure Hodge number. Okay. And it's a well-studied subject, but because we're sampling from the same moduli space of calabi-yaus in all dimensions for the ice cream cones and the sunsets, they have the same mirrors. So calabi-yau mirror symmetry just gives the same mirrors. So as interesting as it might be to use calabi-yau mirror symmetry to reinterpret limiting mixed Hodge structure computations and things like that in the context of these Feynman integrals, it's not going to answer the fundamental question, which is how do you distinguish on the level of calabi-yau geometry between these? Okay, but there's good news. So the good news is there's a version of mirror symmetry that actually applies to families of calabi-yaus. It's called Landau-Ginzburg Fano mirror symmetry. Okay, and the idea is that a Landau-Ginzburg model with superpotential is a mirror to a quasi-Fano variety. Okay. Think quasi-Fano, take a Fano variety and blow it up enough so that it still has an anti-canonical calabi-yau. That's good enough. It's quasi-Fano. So the strategy here is then to figure out, well, what should the superpotential be? Okay, and so roughly speaking, the Landau-Ginzburg model is going to be some fiber-wise compact, I'll draw it with elliptic curves, fiber-wise compact family of calabi-yaus over a copy of C. Okay, this map is the superpotential. And then its mirror to, as I said, a quasi-Fano variety. So this is the package. It comes with the data of a family of calabi-yaus. All right. So theorem, DNV. One, the sunset Motivic calabi-yau manifolds define LG models with superpotential equal the external momentum, in this case p squared. The complex structure deformations of the LG model are now the mass parameters. Okay, that's the sunset. It's naturally an LG model. Now, what about the LG model when we specialize to the all masses equal? Okay, the best studied case of the sunset. Well, that's mirror in this sense to the all ones hypersurface inside P1 to the n, and that's a Fano manifold. Very good. But we can also do it for unequal masses. So the LG model with unequal masses is mirror to weak or singular Fano variants of the Fano manifold corresponding to the all masses equal. Okay. And finally, so with one of the external momenta superpotential, the ice cream cone Motivic calabi-yaus define LG models that are mirror to the quasi-Fano blow up of the all-1 hypersurface in P1 to the n along a codimension 2 calabi-yau submanifold. So it's a calabi-yau submanifold of the anti-canonical calabi-yau in P1 to the n. Okay, so Landau-Ginzburg mirror symmetry is actually telling us something important. It's telling us that we can capture the difference between the sunset tower and the ice cream cone tower using Fano geometry. There we go. Okay. All right. Finally, what about the kite Feynman graphs? So for the kite Feynman graphs, we're really talking about a kite, oops, maybe a kite with a multi-loop sunset in the middle. Okay, and maybe I'll move this around here. So, okay, now I've got a P1 squared through P4 squared. I've got the various masses. I also have kinematics I have to worry about, Sij terms, okay? I want them all. I use them all. I need them for geometry. So, theorem. First, the Motivic calabi-yau Z n-2 of the n-1 loop kite Feynman graph is fibered in codimension 2 by sunset Motivic calabi-yaus x n-4 over a non-toric rational base surface, say S2. Okay, we're not the sunsets anymore. Okay, we've moved beyond the sunset in all dimensions. So what we're seeing now is this fibration still by sunsets, but not codimension 1 fibration like we had before, sunsets fibered by sunsets, but in codimension 2 over a base that's not toric. Okay, but there are explicit topology changing transitions between the kite and the ice cream cone Motivic calabi-yaus derived by matching vibrations. So a classic trick when you're trying to answer the kind of question about when two calabi-yaus are isomorphic to one another is you find calabi-yau vibrations on them, reduce the problem with dimension, but do it with parameters, line up those vibrations to match the parameters, and then you know whether or not they're isomorphic. It's an easy way to prove they're isomorphic, okay? In this case, you play that game and you realize an explicit topology changing transition. So you're actually going effectively continuously in the calabi-yau moduli sense between one moduli space of calabi-yaus and another, corresponding to one class of Feynman graphs and another. Okay, so lessons learned, and this is my last slide. So first of all, the geometry and moduli of Motivic calabi-yau manifolds connect distinct Feynman graphs and their integrals. So for those of you who know a little bit about the early days of string theory, Philip Candelas had this marvelous paper called Rolling Among Calabi-yau Vacua. Okay, so you might call this rolling among Feynman integrals. Okay. Second, there are key roles played by, well, calabi-yau iterated fibrations, and we should hear more about that, I think, in the talk tomorrow by Laura, and by Landa-Ginsburg-Fano mirror symmetry. Okay, and parenthetically, these are linked by a form of mirror symmetry that I actually introduced with Alan Thompson and Andrew Harder, the DHT mirror symmetry links these. Okay, there's actually a procedure for gluing Landa-Ginsburg models. Okay, so gluing, if you like, the families of Motivic calabi-yaus to be mirror to a smoothing process that allows you to go up in dimension in your calabi-yau tower. So it's beautiful and it works out. It actually turns out that when you apply this procedure to the sunsets, you derive the ice cream cones. So it's pretty. And finally, we're finally ready to apply the tools such as limiting mixed Hodge structures, higher normal functions, the sort I studied with Matt Kerr, regulator periods, etc. And this is joint with Spencer Block, Matt Kerr, and Pierre Van Hove to actually study amplitudes. Okay, thank you.
All right, let's take a moment to unmute ourselves and thank Chuck. And then it looks like we already have a question from David.
Well, first of all, a very, very big thank yous to Charles for providing this overarching mathematical perspective. Just two little comments to clear up vocabulary. When you say sunset, I say sunrise, and my good friends Spencer and Pierre kind of got confused and started talking about bananas. When you say ice cream, I say dancer's cap. Now, let's get down to more serious matters. You provided me with the exact word which I needed and fumbled in comments after the previous talk for what I was talking about. You talked about generosity. The opposite of generosity is to be degenerate. I am the most degenerate person in the whole of this conference because I look at the very special, the things that God asked me to look at when calculating the magnetic moment of the electron. And I want to pass on, I think, a very, very deep thought that comes from my good friend, Duco van Straten. He says, when you have a generic algebraic variety, and you go to a degenerate point, not a singular point in the sense of the singularity of the equation, but those degenerate points that Philip and Xenia were looking at in the calabi-yau threefold, then you should be aware that you're touching something very, very special, which can be the degeneration of a completely different algebraic variety. So
absolutely.
Generosity, which is loved of mathematicians, is a clue. And secondly, the final comment I want to make is please, please, please put on chat the link to your October talks so you can fill up my diary, because I really want to hear more about this.
Okay, my October talk. Oh, yes, absolutely. I'll do that. I think I haven't updated my webpage since the epidemic hit, but I plan to include links on my webpage to all that. So that should be easy. That should be easy. Let me just
I was just going to say, we can do that both on the chat and then on the Slack channel, because that'll have more persistence and time.
Oh, that'll be great. So let me just amplify David's comment. So when you're dealing with elliptic curves, you definitely have two kinds of specialization that are really obvious, right? One is specialization to complex multiplication points. And this, of course, relates to all sorts of interesting questions involving rational conformal field theory and what have you, not to mention arithmetic. And then you have degeneration that is actually, if you like, the ADE singular degeneration of the fibers. The degeneration of the fibers into cadaver-type, so they're actual geometrical degeneration. Yeah. So when you pass to K3s, the story is quite similar in many ways. You still have the strength of global Torelli at your disposal. The class of automorphic functions that's involved is richer. But the phenomena, aside from this rank jump phenomenon that I talked about, which we should properly view as passing from one moduli space of lattice polarized K3s to another, it's more or less the same story then, okay? Once you hit calabi-yau threefolds, you get new interesting phenomena arithmetically, you get connections to the Andre-Oort conjecture, you get a lot of really rich interplay between the arithmetic and the geometry that wasn't visible in lower dimensions. And I don't know enough about the physical motivation for some of these questions to know which of these series of structures is going to be most relevant for application, other than to say that we should just investigate them all.
Okay, thank you very much. But I just, if there are any physicists listening, try to be as degenerate as possible.
Okay, so, and I want to take that to heart. So as degenerate as possible means in the context of these families, because I'm contrasting it with the comment you made in the previous talk. Is physics interested in arithmetic specialization? So specialization to points in moduli where the varieties are defined over number fields, or is it more interested in the geometrical degeneration, or both?
Physics is God. God tells us which particular integrals to look at because she does quantum field theory. And so we start with the quantum field theory things. And if we feed you special and degenerate cases, that's not because we've chosen them. That's because God's chosen them when she does quantum field theory.
Sounds good. Then out of respect for her, we should study them all. Very good. Any other questions?
We do have a question from Matt, if he's available.
Yes, thanks. Great talk. So I was a little surprised when you were discussing the ice cream cone, and immediately after that it's the same mold. You went on to try to find ways to distinguish them geometrically. One thing as physicists we care about a lot is being able to find which integrals we can expect to have rational coefficient relations, linear relations between. I'm curious if you had any expectations about whether objects like the ice cream cone and the sunrise would be able to have relations or not, given what you've observed about the geometry. I mean, if it's the same geometry, could the integrals be rationally related, or is that not possible if they have different mirrors?
So this is where things get really fun. So the Picard-Fuchs differential equations, or system, if you like, for the ice cream cones is going to literally be a pullback by a branched cover of the differential equation that shows up for the sunset. Now, that doesn't mean that the Feynman integrals can't have an extraordinarily interesting new behavior, because there's an inhomogeneous part to the differential equation they satisfy. And this inhomogeneous part has an interpretation as a normal function, and it's known through, I mean, I've done some work with James Lewis and Matt Kerr and Shi Chen on this, and certainly other people have in different contexts. It's known that there's a subtle interplay. So I am in no sense saying, and I think Pierre, were you here, would back me up on this, we're in no sense saying that the physics of the ice cream cone is not more interesting than the sunsets. But we are saying, from the standpoint of the underlying Motivic calabi-yau, you're talking about the same individual calabi-yau varieties, individual calabi-yau manifolds. Their behavior in families is a little different, right? And you have to worry about what happens in those families to the extra structures we tack on. I mean, what I've hidden in all this, right, is I focused on the Motivic calabi-yau. I haven't told you which differential forms to mess around with more generally in your integrand, right? I haven't told you about the numerator. I mean, all that is dressing, but it's the essential dressing for a lot of the calculations that you physicists want to do. But if I have to boil it down to what is the relationship proposed between Feynman integrals, Feynman graphs, and calabi-yau geometry, I try to make it as simple as possible. So I focus on the Motivic calabi-yau, the thing which is going to be valid. It's present regardless of what D you pick. I mean, it may be easiest to play with in D equal 2, but it's still there, any D. And then after the fact, after we understand that geometric dictionary, a combinatorial or integral geometric dictionary, then you get to layer on these extra structures. So I'm not going to. So I guess the short answer to your question, which probably should have come up front and maybe did, is that I'm not saying that I'm not saying strongly that there's no relationship, but I mean, it depends on the question you ask, right? Look, formulate the same question about elliptic curve families that you already know at 2-loop, right? If you have an interesting answer there, you know you're going to have an interesting answer in higher dimensions. Let's put it that way, okay? And so the theme of this workshop is elliptics and beyond, and you know, from my perspective, once we have this dictionary with calabi-yaus, we're ready to do transcendental algebraic geometry with these calabi-yaus. And that means we're going to have the periods, and sometimes we'll get lucky, like in these cases, and the calabi-yaus will be iteratively fibered, in which case you can do iterative constructions of Picard-Fuchs equations and periods. And this is near and dear to my heart. You know, it's a beautiful structure of these that one can explore and exploit. But it's like David said, right? When she tells us what to do from the physics, we'll be ready to set up the computations, okay? But then classes of questions, right? If as physicists you feel it's important to know, I don't know, something about the transcendence degree of an extension of field, I don't know, something like that, we can reformulate that now in mathematical terms. I mean, look, the workshop that I'm giving this Picard-Fuchs differential equations course at is on model theory in logic, okay? So we build these structures and they're useful for physics and they're useful for model theorists and they're, you know, whatever. So I'm trying to lay the foundation. I've spent about 2 years laying the foundation of what I view as, you know, the bridge to calabi-yau geometry, with the understanding that if it didn't work, I would have maybe wasted 2 years. But I think it's working. And I think the features of calabi-yau geometry and moduli are showing themselves now. So yeah, let's just keep going.
It looks like we also have a question from Paul Constantine in the chat.
Okay. Do I have to look at chat or?
No, he's just curious.
Hello. Yeah, I have a curious question. Just in general, I'm coming not from the I'm coming more from the calabi-yau direction, and I was wondering so one thing I didn't understand was when you say, for example, in this multi-loop sunset diagram, a computation where you show which parameters you need in your Hodge numbers. I think you said something like H11 or so must be n, or would correspond to n, and oh no, sorry, H11 was this longer formula in n, and then you had H n minus 3,1.
Yeah.
So what I didn't understand is that you later said that mirror symmetry doesn't really like mirror symmetry of calabi-yaus doesn't really buy you anything. But I mean, I would not expect that for like a general calabi-yau that these Hodge numbers stay the same. I mean, you would now in the mirror.
No. So when I said mirror symmetry doesn't buy you anything, it doesn't buy you anything to figure out the difference between the underlying geometry of the sunsets and the ice cream cones. That's what calabi-yau mirror symmetry won't do. Okay.
Yeah, okay.
No, look, mirror symmetry is. I spent most of my career working on mirror symmetry and things related to it through calabi-yau geometry, and mirror symmetry is marvelous and powerful, and you can recast many of the questions you ask about periods into questions about counting curves in the mirror, and that's beautiful and deep, right? For many reasons, as I said, model theory and physics. But having said that, it's not. I mean, a message from that corollary is that it is naive to expect that the moduli space of calabi-yaus we're accessing from a given Feynman graph is going to be enough to characterize its properties completely. It's the morphisms to that moduli space that also have to be taken into account. Okay. And then from the raw standpoint of, look, I want to be able to turn a classification problem in combinatorics and physics into a classification problem in geometry. Well, I can't do that with calabi-yau moduli spaces as stated, right? So I turn it instead into a statement about the mirrors of the associated Landau-Ginzburg models. Now, I'm not claiming I've done that yet in all, I mean, you know, it would be marvelous for me to be able to say, yes, I have firmly established that all of Feynman integration is really a story of ... Okay, all was really a story of studying a particular class of you know, anticanonical pairs and Fano varieties, blah blah blah, with all the right terms. We're headed there. We're headed there. Okay, but we're nowhere near being able to say it. But with these primitive examples, and again, they're not just two loop examples, right? These are all loops. These are towers. Okay, with these basic examples, I think we have enough to be able to say that the relationship between Feynman integration and Motivic calabi-yau geometry is robust. I have no reason to believe now that we can't associate a calabi-yau to any Feynman graph that is going to have similar properties, and that natural operations, yet to be described in detail, among Feynman graphs, natural in the sense of the combinatorics and the physics, will manifest themselves naturally in terms of the geometry of the corresponding calabi-yaus. So now just another word about that Hodge number computation, because I think there's been some confusion in the literature a bit about how these things are done. The Hodge number computations that you do are delicate. They're in general going to only apply to the genericity case, the generic case. And in fact, they often aren't computing what you want. You know, they'll compute some kind of stringy Hodge number, and then you have to argue that it's actually computing the real Hodge numbers. Also, there's this issue of non-closed form formulas. And that's why you can't just look up in Batya or Borisov and get the kind of answer I wrote down. You actually have to go to my first paper with Novoselicev, and then we had to do this delicate induction. And we did it, you know, it worked. But we had to use really special properties of polytopes. I mean, it was really kind of cute to work it out. And again, only because it was generic was that even relevant. So in general, I don't know. I mean, the message from the kite, it has a beautiful calabi-yau structure. It's fibered by sunsets in codimension 2 over a base, but the base is not toric. Okay, so you're not going to be able to use torically induced vibrations, the wonderful tool that we use all the time in applications to physics. It's just more subtle. It's just more subtle.
And also just really quick, because that was also a quick question. So you showed, for example, like 2 Hodge numbers there, but like, I don't know, if you go to 4-folds or whatever, you have, you get an increasing number of new Hodge numbers. So is there any kind of match or idea that this would correspond to anything, or?
Well, okay, so Hodge numbers in general for calabi-yau manifolds, I mean, for calabi-yau threefold, there's only the 2 interesting ones, and they have clear interpretations, okay, geometrically in terms of moduli. For higher dimensions, you lose, I mean, you know what they are, you know what they mean in terms of raw definition, right? You can define them in terms of properties of cotangent bundles and tangent bundles, whatever, but they lose their sort of intuitively natural interpretation as just counting moduli, these other numbers. And since the question we were talking about was really about properties of the moduli spaces of calabi-yaus, we focused on those 2. The results with Novoselicev actually give us a broader class in all dimensions of Hodge numbers that we can compute. It's just, I don't know what they're good for the purposes of geometry or physics. But again, if she tells us that you need to know some other Hodge numbers, then we may be able to get them and then have that interpretation.
Sure. Great, thank you.
All right, with that, perhaps we'll close the official session, although people are welcome to stick around and chat a little more.